Good morning to all our participants. Thank you for joining us for day 2 of the software conference and for joining us here in the hearing room 1 for session WB1. We're excited to start our session with a presentation from Zhou. He'll be from Argonne National Lab. He'll be presenting on reliability assessment of power grid operations considering correlated dependency from gas pipeline delivery over extreme weather. Zhou, please. Thanks.
Good morning, everyone. My name is Zhou. I'm from Argonne National Laboratory. And this work is a collaboration with my colleague from Argonne with different background, including power grid, pipeline, gas pipeline infrastructure, modeling, mathematics, and environmental science. Next slide, please. So here is the outline of my presentation. First, I will give a couple of examples about why this study is relevant and what is the specific research question we are interested. And then I introduce the workflow to capture the climate and the weather impact on grid reliability. That include the weather-dependent grid inputs translation, data pre-processing, and also system reliability assessment. And then I will give a case study and some preliminary results. The last part is a conclusion. Next slide, please. Okay, so in the recent years, we have been seeing more frequent and severe weather-related events. Here are 2 examples. The first one is the winter storm Elliott back in 2022. So there are more than 90,000 megawatts of unplanned cold weather-related generation outage, and 60% decrease of gas production across the whole lower 48 states. Some region even has more declines by 23 to 54% of the decrease. And there are more than 1,700 experienced units outage and experienced 3,500 plus outages, deratings, and or failure to start. And 825 units were natural gas-fired generation units. So here in the figure, we can see that with this bottom left, we see that this is the gas production. For the total US lower 48 states, we see that there is a drop just for that during for that day. So, and then on the top right, this is the outage by fuel type. So we see that more than half of that is from the gas power plants. The bottom right figure shows with the decrease of the temperature, we see more outage in terms of capacity from thermal power plants. Next slide, please. Okay, here is another example from Texas back in 2021. Where similarly, so besides wind power outage, we saw a significant outage from thermal power plants. So about 4,700 plus megawatt out of 9,300 plus megawatt loss actually from because of the freezing issue, and more than 4,000 megawatt of natural gas-fired generation experienced outage or derates or failure to start. So next slide, please. So here comes the research questions. The first one is what are the major weather-dependent grid inputs that may impact operational and planning decisions from a reliability perspective? And how is the power grid reliability impacted by those weather-dependent inputs? What consequence could be if misestimate weather-dependent inputs? How to incorporate them into the existing grid decision tools? How we incorporate the weather-dependent inputs, and how the model could respond to those grid events, especially those extreme events that are out of the normal operational conditions. And the last one is about how to characterize the extreme weather events, hazard events. So how to coordinate the operational planning of the coupled complex system. For example, for those low probability, high impact extreme events, how should we incorporate it into the long-term planning? how we take those uncertainty representation into the planning or operational models. Okay, next slide, please. We have done a survey from the literature about all the study about the links from the weather or climate to the electricity or gas pipeline network. So this figure shows the impact on the electricity system. So on the left hand side, so we have the single thread or the combined thread. The single thread means that is from the single weather variables. For example, cloud or cold, that is temperature, or cold or heat, that is about the temperature. Or wind drought, a strong wind, so that is from the wind speed. We also have this combined thread, for example, the combination between the cloud and the wind, or cloud and the temperature, or temperature and the wind. So these have different impact on the electricity, different components of the electricity system, like generation, storage, transmission. So for example, if we take the solar PV as example, so cloud may have impact on the solar generation. A combined event like clouds plus wind also have a significant impact on the solar generation. So another example is the gas power plant. So we see that it will be impacted by extreme high temperature or low temperature. With a combined event, it will be impacted by, for example, windstorm, clouds, freeze, plus wind. Okay, next slide, please. So this table summarizes the impact to the gas pipeline system, and the same on the single threads and the combined threads. But on the component side, so we have the upstream, midstream, and the downstream of the gas pipeline system. So for example, for the gas production, it will be impacted by cold weather, strong wind, and also some of the combined threads. So this is what we summarized from the literature. Next slide, please. And the coupling of the grid and the gas pipeline network. So the two systems are deeply coupled. So for example, on the grid side, so a gas power plant served by the gas pipeline system, and takes the ISO England and the PJM example, they have a significant portion of the load actually are made by the gas power plants. On the pipeline system side, so some pipeline components are electric powered. For example, the compressor station, more than 10% are electric in the US, high in the Midwest, California, and some other areas, based on the literature. So the weather-caused events may impact both systems simultaneously or from one side spread to another side. One example is the extreme cold weather may cause component failure on both ends simultaneously. Another example is that extreme cold weather may cause high gas demand, then cause disruption of the contract delivery to gas power plants. Next slide, please. So here comes to the focus of this study. The first that is we focus on the short-term operational reliability on extreme weather condition. And then we look at the interaction between the two systems on short-term operations, mainly on the gas delivery to the gas power plants. So this could be caused by the pipeline components failure, can also be caused by the gas delivery curtailment due to high demand from higher priority customers. And then we particularly look at the extreme cold weather impact. So the high summer power plant outage because of the extreme low temperature, and also higher probability of gas delivery disruption. Next, yeah, thanks. Here are the tools that we are using in this study. So we have the grid and the pipeline operational model on the grid side. So we have this power system economic dispatch and reliability assessment, which is an in-house tool called Argonne's low carbon electricity analysis framework, ALIF. So this tool has a suite of models from short-term to long-term, but here we only use the short-term operations, the daily system operation, economic dispatch, And the objective is to minimize the total operational cost subject to constraints of like generator physical constraints, network flow constraints, supply demand balance constraints. So we have the two segment scheduling. The first is the day-ahead dispatch, assuming all units are available. And then in the real time, we do redispatch, account for outage, gas delivery disruption. And then we have, in terms of the weather-dependent grid inputs, we look at the electricity and gas demand, summer power plant outage, renewable generation. And for the reliability criteria, we look at the expected unserved energy. So on the pipeline side, our model, we also use an in-house model called NG Transit. It is a pipeline operational optimal operation. So it is also a short-term model tool that look at the daily pipeline system operation. So it has a sub module of the gas pipeline system, including the junction, pipeline, compressor, load, and pipe link. The objective is to minimize the total compressor power and gas delivery shortfall subject to the constraints like the mass conservation, pipeline, max allowable operating and pressure. And the model is also tested with different disruption scenarios. Next. So here is the overall workflow and how we do the coupling of the gas power plant. The power grid and the gas pipeline system under the weather impact. So we start from the left-hand side and different weather variables or other factors is the main input to the whole coupled system. So it has impact on the so for example, on the bottom side, that is about the electric system. So the weather impacted input, including the electricity demand, renewable generation, summer or renewable outage, and also transmission outage. And this input would get into the ALIF, which is the dispatch model, also the reliability assessment model. And then on the top side, that is the pipeline system. So we consider the gas supply, the impact, weather impact input, like the gas supply, gas demand. This would be the input to the gas pipeline operational scheduling model. And then the model would estimate the gas delivery risk to the power system operational model. Another link is that when the generation, when the power grid scheduling is done, so you can send the scheduling of the gas power plant and also the gas consumption to the pipeline operational system. So that will be combined with the gas demand from other long power sector. So this is the overall workflow. Next slide, please. So, okay, so here is one example how we do the translation of from the weather variable to the grid input. Especially, this is the temperature dependent summer power plant outage. So here we use the LERC generation availability data system data to train the regression model and to train a regression model to get the weather dependent summer power plant outage rate. And this model is trained by different technology type. For example, coal power plant, gas power plant, nuclear power plant all have a different regression equation. So the main logic there is that at any hour, depends on temperature, the summer power plant status can be from available to outage, or also from outage to available, outage to outage. So we use that data to train this regression model to get the probability of the status change from one status to another, and then the results here is validated with some other literature listed here. So it's pretty close. Yeah, next slide, please. So here is the overall workflow that we translate the weather to power input. So here we particularly focus on the solar generation, wind generation, loads, projection, and the thermal power plant outage. And we mainly use the weather variables on the left-hand side, including the solar irradiance, temperature, pressure, air pressure, wind direction, wind speed. And some of the grid input would take a multiple weather variables. Some just use one variables, like the thermal power plant outage just use the temperature. Next slide, please. Oh, okay. Yeah, so another thing is about the uncertainty modeling. So for the extreme weather scenarios in the long future, like in the middle of the century, we definitely want to know for that scenario, what is the probability, what's the uncertainty around that scenario. So this is the main reason that we want to use the uncertainty modeling around the identified future scenario, weather scenarios. So one way to do that is we rerun the climate model to generate a set of future weather climate output, but that is very computationally expensive. So here we use a statistical surrogate method that we generate new realization of the variables. Specifically, we use a methodology called the moving window Bayesian generalized addictive modeling. So this is a statistical non-parametric regression model, but we use the Bayesian inference to update the parameters based on the input data, the available data. And there's a couple of features. One is that we have this moving window approach to move from one dimension to a spatial time dimension. So basically, we can consider spatial temporal correlation, and then we can also consider the correlation among different variables. Here are examples to show that how the uncertainty is around that specific weather scenarios in terms of the wind temperature, wind speed, and also solar irradiance. They are plotted separate plots, but when we estimate them, actually we do consider the correlation among them. Next slide, please. So in terms of the climate data, so we use the so the data source is from Argonne. Link is here. So we look at the whole. The data set is covers the whole the continent of the U.S. And also most of the Alaska and Canada. But we only look at for this study. We only look at the northeastern region of the United States. So it has a 3 period. 10 years from the past, 1995 to 2004, 10 years from the middle of the century, and 10 years at the end of the century. And for the global climate model, so we have three models here listed here. We also consider different CO2 concentration pathway, especially for the weather variables. So as I just mentioned, we particularly interested in the temperature, solar irradiance, and wind speed. Next slide, please. Okay. So for this specific study, as I just mentioned, the coupling point is the gas power plant. Since we particularly look at one gas pipeline system is Algonquin, which serves the Connecticut, Massachusetts, and Rhode Island. So here we look at this. So this is the left-hand side is the pipeline system. The right-hand side is the power grid, and in the middle is where those gas power plants located. Next slide, please. Yeah, let's skip this now, please. So here is one specific example how we do the translation from the solar power plant, solar irradiance to the solar power plant generation specific to this region. So we get the data from the, so we have the weather data. We also use the PV line. and we calculate the solar irradiance, the solar generation from each individual PV farm, but that is from existing PV farm, and then we aggregate that to each county, and then eventually aggregate to the state level for this particular study. Next slide, please. So this slide shows how we identify the hazardous events. So we have two methods. One is a machine learning based method, specifically the isolation forest. Another is statistical ranking. So here the slide shows the bottom shows that how for those specific data that we identify with extreme weather events, how the temperature, solar irradiance, and wind speed look like. Next slide, please. This is the results for the uncertainty modeling part. So with that specific selected, identified hazardous day. So this slide shows the uncertainty modeling of that for that day in terms of those three variables. The top is the mean from the climate output data. The downside is the posterior mean from the generated scenarios. So the uncertainty is represented by the set of the scenarios. For example, here we have 1,000 scenarios. So we calculate the average from that 1,000 scenarios, compare that with the actual the data from the climate model output for that specific day. So we see that this is pretty much a match to each other. Next slide, please. And so, unfortunately, we have not finished that real coupling bit from the gas pipeline system to the power grid. So here we have we do a sensitivity analysis. So for the gas power plant outage due to fuel delivery disruption, we assume that it is 0% all the way to 100% of the gas power plant outage due to the disruption of the fuel delivery. So the results here to see that for that specific pod day, so we do not see any load curtailment all the way until we start until 50% of the gas power plant is outage due to the fuel delivery disruption, as showed under the table. So the observation here is that more capacity margin during winter storm because of the peak demand is much lower than the summer peak. And also, if not consider gas delivery outage, load curtailment probability in winter is very low because of this wind peak demand is low. So for that specific day we choose, the peak demand is about 20% less than the annual peak demand, which is in the summer. So if a winter storm causes severe gas delivery disruption, so we will see a great impact on the power grid reliability. Next slide, please. So here are some future work. The first thing is that holistic uncertainty modeling and scenario generation on compound extreme events. So this would involve a large number of samples and computational issue. The second future work is about the gas delivery disruption derating probability. So right now we assume that is the disruption either on or off. But for gas power plant, because of the pressure, it can be partially disrupted. So we probably it's better to use derating and estimate the probability. The last one is the transmission outage. So we do not model that in the current study, but that is also one important factor may impact the reliability. Yeah, that is all I have.
Thank you, C. Sorry, do we have any questions from our in-person audience? Yes. Please introduce yourself.
Hi, Celine Linkara from Newton Energy Group. On one slide, I saw that you only listed 10-meter wind speed in your weather variables. So how did you deal with wind speed at different elevations for wind farm modeling? Did you have to interpolate somehow?
Yeah, we actually did some experiment on. So you mean the wind speed at different height, right?
Yeah.
Yeah, we did some experiment that see that if we just use at the 10 meters, the results is pretty close. So we just use that. Yeah.
Do we have any questions from the virtual audience? Any other questions from our in-person audience?
This is Jeannie Zhao from ISO New England. So just a clarification question. So in your presentation, you mentioned your lab has two models. One described the power system dispatch, the other described the pipeline network. And then these two applications seems to need to work together in order to reflect the coordination. So can you elaborate a little more? Is this a iterative process when you're trying to mimic the interaction between power system and pipeline system?
Yeah. I have that flow chart. So basically, we can do that in multiple iterations to get a good solution. But here we just use one iteration. So basically, in the day ahead, when we have this, we have the day ahead scheduling. So we know the gas pipeline output. So we can translate that into the gas demand. This information would pass to the pipeline operation. The pipeline operation would take this as part of the gas demand because there is also another part of demand from long power system. And then the gas pipeline system would do the operation. But this is on the day ahead, but in the real time, because of the outage, so the system need to redispatch. So it will have a different dispatch scheduling. So we will see that whether the gas pipeline system would accommodate this change. So this is one impact on the disruption. Another one is the weather dependent gas pipeline input. So the gas pipeline system also need to estimate the gas demand and gas supply injection to the system because of the extreme low temperature. So whether that part also have the impact on the power grid. So that is another connection to the power grid.
Okay, thank you very much. A follow-up question, you also mentioned in the future work, you're trying to estimate the derating factor due to the pipeline constraint. Yeah. So how is that related to this iterative, not iterative, the process you just described?
Yeah, so, okay. So, the major input from the gas pipeline system to the power grid is the disruption risk. The disruption risk can be modeled either as an outage, totally disruption, or because of derating, because of the pressure decrease. So the gas pipeline operation can model that. So mostly because of the outage, it could be a total outage, or could be just the pressure cause that is kind of only partial output the generation. So we take that as input to our input. So either outage rate or derating rate.
Okay, thank you very much.
Any other questions from our in-person audience? Any questions from the virtual audience? All right. Thank you, G. One more round of applause. Our next presenter will be a virtual presenter, Tomas Valencia Zuluaga from Berkeley, and he will be presenting on parallel computing for stochastic power system capacity expansion planning. Thomas.
Hi, good morning. Thanks for being here, and thank you for tuning in for this for virtual. My name is Tomas Valencia. I just finished my PhD in operations research at UC Berkeley, and I'm starting postdoctoral research at Ortega-Vazquez National Lab later this month. So I'm very happy to be here to be able to present this work on that we've done during part of my PhD in collaboration with Ortega-Vazquez National Lab with David Musselman and John Paul Watson there while working at UC Berkeley on Professor Lauren. So yeah, let me get started with some motivation for this work. So as we all know, climate impacts are increasingly affecting the reliability of power systems. This is coming both from changes in routine weather patterns, so be that the shifting of wind and solar patterns, and that affects the wind and solar power plant availability, the shifting of temperature baselines and how that affects electricity load and the availability of water, and also in the frequency of extreme weather events, so wildfire, hurricanes, floods, and heat waves. And so one way of addressing all of this and achieving reliable systems, which is something we want to do, is including this impacts into the expansion planning process. And so what we want to do with this project is really increase the level of detail in our capacity expansion planning model and compensate for this additional complexity by taking advantage of high-performance computing clusters, of parallelization in supercomputers. So let me get started with that. Next slide, please. Okay, so the power system capacity expansion problem. There are many different models that could be formulated under this umbrella term. So let me give you an overview of the one we work with in this project. So the capacity expansion problem we work with is a joint generation, transmission, and storage expansion problem. So we are deciding where to build each type of these three resources to minimize the overall cost of the system, that is investment cost and operating cost. Next slide, please. This is a classic uncertainty problem where we're making decisions now. So where to invest, how much to invest in each of these types and where. And those decisions are going to impact the cost we incur for many years into the future. And those future costs, these operating costs, are uncertain. And of course, they're uncertain in many different dimensions. So for this project, we're only going to concern ourselves with climate dependence or climate and weather dependent uncertainty. And that is mainly availability of resources and the behavior of electricity demand. So of course we cannot predict the future and try to again guess what's going to happen and plan for that. But one thing we can do is try to minimize the expected operating costs, its uncertainty costs, and that sets the stage for a stochastic optimization formulation, which is what we're going to do. We're going to solve a stochastic optimization problem, and as this little formula that I have here hints at, we're going to do that with a two-stage stochastic optimization problem. So I'm not going to go into full detail of the mathematical model we're using, but I will give you some overview of it. So yeah, let's get started with that. Next slide, please. Okay, so this is a quick overview of the mathematical model we have. And this is based on an existing capacity expansion planning model from Pepe, Go, and others in 2016. So as I was saying, it's a two-stage stochastic optimization problem. In the first stage, next slide. In the first stage, we have the investment problems. So next, first the generation investment variables. Next slide. Then storage. Next slide. Thank you. And transmission. Next slide. Okay. And in the second stage, we have the operating problem, which is as I said, where the uncertainty lies. So this is going to be captured through a discrete set of scenarios. Next slide. And each scenario has an associated probability. Next. Yeah, thank you. And what each scenario corresponds to is a representative day in this planning horizon. And so each day is going to be a multi-period operational problem. Next slide. So we have over a set of periods within that day. We take into account the costs of the operational costs of generation. Next. Storage. Next. And eventually the cost of shedding load if we're not able to serve all load during some of those hours. Next. Yeah, thank you. Okay. And in terms of the constraints, I'm representing them here in this very compact way with two categories of constraints. So first, next slide. The construction limits. So these are our constraints that are only enforced on investment transmission variables. So how much can we build of each type at each location? And the second category of constraints, next, is operational constraints, which are dependent on each of the scenarios considered in the set, where all the physical limits of the equipment, the restriction of being forced to serve demand or explicitly shared net, and all these constraints are considered. Okay, so in this very, very high level view, it's a linear two-stage stochastic optimization problem. Last thing I'll say about this mathematical description is about the domains. So next slide. So storage investment variables generation investment variable for renewable types, and everything in the second stage problem, so all operational decision variables are continuous. Next slide. The generation investment variables for thermal types are integer. Next slide. And transmission investment variables for transmission elements are going to be considered through a set of investment candidates which are either built or not built, so they're binary. So what we have when we put everything together is a two-stage. Oh, go back one. Sorry. So what we have when we put all of this together is a two-stage stochastic mixed integer linear optimization problem. And so this is the problem we're going to work with. Now, as I was saying before, this is an existing model in the literature, which with some minor modifications. So the challenge here when this project started was tackling two dimensions really. Next slide. So the first dimension we wanted to increase the level of detail in to really tackle this climate reliability challenge was increasing the geographic resolution. So on the left-hand side here, we have the WEG 240 bus system, which is a very common representation, a very common power system that we encounter in the literature of capacity expansion planning. And it's a 240 bus representation of the entire Western interconnection of the US. On the right-hand side, we have the California Test System, CATS system, which was developed last year at the University of Wisconsin-Madison at Professor Lina Rold's group, which has almost 9,000 buses just for California. And that's the model we wanted to work with for this project. So you can see just from the size of the system, by the increasing the geographic resolution, the size of the problem, of the mathematical problem we're trying to solve, increases significantly. And the second dimension, next slide, please, comes from this set of scenarios we want to include in the stochastic optimization problem. So I'll give you a quick overview of where this is coming from. But yeah, just to make it explicit, so this part is not my work. This is part of a macro project at Lawrence Livermore, and it's a different part of the lab that's been working on this project. But yeah, the idea is taking a global circulation model, which is a atmospheric thermodynamic model of the entire planet, and downscaling it, focusing on the area of interest. So for our project, it's going to be California, and by doing that, focusing on an area, increasing the geographic resolution, and obtaining outputs. So outputs for the variables that are going to be of interest to us. So things like wind speed, solar radiation, humidity, temperature, which are much finer grade for several decades into the future. So for this particular example that I have here, up to 2045. And so we take these variables and we put them in what I represented here with this little gearbox, which is a system based on the Andrew system advisory model, which translate these variables into profiles of potential generation for each technology. So for wind power plants, solar, and load profiles for the electricity demand at each location in the grid, for each period of each representative of each day in this target horizon. So for this particular example, this will be the year 2045. And so because there's a lot of what we might call uncertainty around these models in just locking into one target year, you do want to include perhaps several years around that target year that you're planning for, possibly different parameterizations of the model. So in any case, what we want to make sure that we're able to do is include a large number of scenarios so that all of them are considered within the pool in our stochastic optimization problem. And this is the second dimension where we're going to have a computational challenge because we have a much larger system with a very large number of scenarios. So we put these two things together. we have a very large scale optimization problem we're trying to solve, which we can't really just throw to a solver, an off-the-shelf solver as it is. It's just too large, so we will have to decompose. And so let me say a few words about the algorithm we're going to use for doing that. Next slide, please. So we're going to decompose this problem by scenario using the progressive hedging algorithm. Just to make sure that we're all on the same page, I'll say a few words about it, a quick overview of what the algorithm does. So what we have here is the optimization problem we're trying to solve that I just went over in just this very compact form, where we have investment costs, operational costs for a set of scenarios, and these two constraints that I went over before. And we're going to follow 3 steps to decompose it. So the first step, next slide, please, is going to be to replicate the first stage variables, so to make a copy of these first stage variables for each scenario, and add the bottom constraint on the right, which makes them all equal to each other, which we call the non-anticipativity constraint, so that the problem on the right is the same as the problem on the left. Next step, we're going to get rid of that constraint that we just added. Next slide, please. Okay. Of course, once we do that, the problem on the right is no longer the same as the problem on the left. But what we do is, next slide, add a penalty to penalize scenarios for not agreeing with each other, so as to make them agree as they were in the original system, and make sure that they do represent the same thing. And why do we want to do that is because once we get rid of that constraint on the right, we got rid of the only constraint that was coupling different scenarios together. So we can actually solve them independently. Next slide. Next 2 slides. Okay, thank you. So we can solve them independently. And if we have a supercomputer where we can do this in parallel, we can solve them independently simultaneously. And so we can do this quickly enough that we can solve the entire problem. So that's the main idea. What that translates to in the case of our capacity expansion model, I'm going to give you a quick example of that. Next slide. So yeah, we have a very small example, as I was saying. Different scenarios correspond to different representative days in the target horizon that we're planning for. So consider we have 2 days. One is a rainy day, one is a sunny day, and we're trying to solve this two-stage stochastic optimization problem. So what we're going to do is decompose, next slide, and solve each scenario independently. Of course, when we do this, initially we are uncoupling the 2 scenarios, and we haven't added any penalties, so they're going to come to different solutions. Next slide. So for the rainy day, of course, the optimal solution is going to be build lots of hydro dams, because that's the resource that is most readily available. For the sunny day, the solution is going to be, let's just build lots of solar panels, because that's the resource that we have the most of. But this is not good. Next slide, please. Because they're supposed to represent the same investment plans, so they should be equal to each other. So what we're going to do is what I said earlier. We're going to add a penalty term. Next slide. Where we penalize each individual subproblem for not agreeing with the average across all scenarios. So we're just penalizing subproblems for not agreeing with each other, and we're going to iterate and update that penalty until after a certain number of iterations, we come to the same investment problem. Next slide. And at that point, we're done. Next slide. Okay. Next slide, please. So yeah, few caveats of this approach. So the progressive hedging algorithm has guaranteed convergence and optimality in the convex case only, because we do have mixed integers and binaries. Our problem is not convex, so this is just a heuristic. We don't have guaranteed convergence or optimality, but some variants of the algorithm exists to accelerate convergence and to obtain lower and upper bounds as we go along. So even though we don't have guaranteed convergence to an optimal solution, we do know how good our solution is, and that can be a good enough heuristic, as we're going to argue with the test that I'm going to show you next. Okay, so let's see how we implement this algorithm on the model that I just showed you earlier. Next slide, please. What we use for this implementation is MPI-SPPy, which is a tool that's been under development for a couple of years now for solving stochastic optimization problems using Pyomo, the widely used optimization modeling language in Python and MPI. So few features make it this a very useful tool to use. I'm going to focus on two of those. First is it makes implementation in a high-performance computer very easy because it takes care of all the communication that needs to happen between the different cores. And the second thing is what they call the hub and spokes architecture, which is what I'm trying to depict here, where we can group all the cores that we have access to into three groups. A group runs the algorithm that I just presented, which we call the hub. It is in the center, runs the regular progressive hedging algorithm. And another group, which is here represented in red on the right-hand side, may be solving, say, a Lagrangian relaxation of the problem, and so comes up with valid lower bounds on the optimal cost of this investment plan. And you could put a different group of cores on the left-hand side here in blue, testing feasible candidates of the investment plan, which comes up with valid upper bounds of the investment of the optimal cost of the investment plan. And when you put all this together, you have lower bounds and upper bounds. We have an optimality gap, so we have an idea of how good the best solution we found so far actually is. And so when we test this on the test case that I showed you earlier, the California test system for a target here of 2045 in this particular example. Next slide, please. This is what we obtain is as we increase the number of scenarios, so in this example here from 10 to 360, we do observe what I was describing earlier, which is upper bounds going down and lower bounds going up. So we have a narrowing optimality gap that gives us an idea of how good our solution is as we are running the algorithm, which we can then use as criterion for terminating the algorithm earlier, which is often one of the shortcomings of this technique is that you know how to terminate. That would be one way to do it. Next slide, please. And in this test that we've run, I'm presenting here, we found very encouraging results where really by exploiting the resource, the computing resource that this supercomputer gives us, by keeping the number of cores dedicated to each scenario constant as we increase the number of scenarios, we're capable of solving to a satisfactory optimality gap of around 2 to 4%. In a reasonable time of 3 to 4 hours, even for the largest instances, which is something that's really satisfactory for this long-term planning problem in such a large scale. So sorry. Next slide, please. So yeah, so just to show you a few examples of what the solution looks like, what this tool creates, and what the output of the tool is. This is what the optimal investment plan in transmission looks like for different number of scenarios for the test instance that I just mentioned. So California 2045, and we don't see a ton of difference between the left and right here. We don't expect to see drastic differences, but we do see some differences in the investment plan in the north and around the LA area. Next slide. Similar story for when you do the generation build out. We don't see a ton of difference as we increase the number of scenarios when we look at the aggregated generation build out. But when we look at the location of those generators, next slide, please. We do see some difference in them being less concentrated around the urban areas in the south of California and more spread out through the Central Valley as we add more and more scenarios, as we see here in the bottom right map. Okay, so yeah, so this is just one example to give you an idea of what the output of the tool looks like. And I'm almost at time, so yeah, next slide. So yeah, so where this project is going and what we're working on next. So the one goal of this project is to release the software. So if you were interested in this, keep an eye out for that. This software will be released probably in the second semester of this year. And in terms of the model and data, how we see that this moving forward, we are improving the California test case that I just showed you. What the tests that I just showed you are on a network flow formulation of power flow. We have ongoing work in the DC optimal power flow and AC optimal power flow formulations, which would improve the accuracy of the model, and we should have some results on this very soon. Of course, a very important part of this project, even though we have the ability to include a large number of scenarios, as we just saw, is scenario selection. So that's also an active branch of this project. And finally, we have in terms of the algorithm, we have identified a lot of potential in using a asynchronous version of the progressive hedging algorithm, since there is a significant difference between the most complicated scenarios and the others in terms of solution runtime. So that's also an active an active branch of the project for future work. And with that, yeah, I want to thank you. And next slide, please. And, this is not the updated slides. Okay, yeah. Okay, thank you, and I encourage you we have a paper recently about this project, so I encourage you to look for it. Had included it here, but yeah, sorry, it was the other slide deck. But yeah, so happy to take any questions. Thank you.
Thanks so much, Tomas. Do we have any questions from the in-person audience?
Hi, my name is Siva from Cornell. I'm actually curious. I think around slide 31, I'm not too familiar with the progressive hedging algorithm, but I'm actually curious. So you're removing the non-anticipativity constraint and then putting it as a penalty in the objective function. So then would X be in the continuous space, or would it actually still be a binary variable? And if it's in the continuous space, how do you actually translate it into decisions?
Yeah, great question. Thanks. So we keep it whatever the original domain was. So for those variables that were continuous, and for those variables that were binary, it is binary. Of course, what you're saying is true. So once you average across scenarios, you may very well find that the average no longer is a binary or an integer if it needed to be. So the average may not be an integer. But when you're testing feasible candidates, you do make sure, and there's like a few heuristics for picking one. You either do the most common ones are either rounding whatever the average is to the nearest integer or binary, or just picking the solution from one specific scenario, which is guaranteed to be in the original domain, and test that for all others. And there are a few, common heuristics for doing that. Those are the two most common ones.
And this is Zhou from Argonne National Lab. So could you elaborate a little bit more about the how you generate the scenarios?
Yes. So for the scenarios, so the original global circulation model was run for several decades into the future, and so from this model, along with the downscaled California originally refined model, we have a time series of several decades of all the variables that are of interest to obtain the generation availability and electricity load for each period of each day for whatever the target of interest is. And so what we have here is a pool of days for that target here. And then how we picked, as we reduced the number of scenarios from that pool to whatever the number I showed you was, 20, 50, 100. In this particular test scenario that I just showed you, I just used k-means for selecting that number. There's a different branch of the project, not the part that I'm working on, but where we look at a more sophisticated ways of picking, especially scenario outliers, because that's something that we know we are aware of that we lose when you use k-means, is those outliers where extreme weather events are most likely to be represented. So we have a different branch working on saving those outliers. But for what I just showed you here, it's just k-means. Okay,
so you do not consider the outliers. They also have very low probability.
Yes, so that we know it's a totally a non-trivial question. Once you identify those outliers, what probability you assign to them? Right. So in what I just showed you is just k-means, but that's an active question of what we're working also on in the in the project.
Okay, thanks.
There was a comment that the model is an E3SM river, a 3-kilometer resolution in California. We have some virtual questions.
Yep. So the first question is, what if a constraint is over the entire set of scenarios? For example, a reliability constraint on the expected unserved energy over all scenarios. How would decomposition/penalization work?
Oh, great. Thanks. Thank you for the question. So yeah, that's actually something that I didn't, I completely swept on the rug there, but that's in the original formulation of model that we're working with, that we have such a constraint in particular. So what you just mentioned is an example, or also a renewable portfolio standard would also be an example of that. So a couple of ways of addressing that. One is just by dualizing the constraint, which is something that we tried. And iterating on the value of the multiplier until the constraint is satisfied, or making it a soft constraint and making it so that you have to satisfy it in every scenario with some penalty that you need to tune to obtain a satisfactory solution. So yeah, those would be the two techniques that we tried for the constraints that we had of that nature. Dualizing or making them soft, and then tuning the multiplier to obtain something that we're happy with.
Thank you. There's a question from the room.
Matt Musto, New York ISL. Just a quick follow-up on the continuous variable and then setting to an integer. Is that where the optimality gap that you were talking about was? Is it as simple as that, or is there more to, basically, how are you determining how far you are from the optimal with the actual solution? I think you were like between 2% and 4% in most of the scenarios. How are you measuring that?
Okay, so what we have is, so to come to the first part of the question. What in some sense that gap is coming from the fact that we have integers and binaries in the solution, and so how we obtain those bounds is so the lower bounds is by solving a Lagrangian relaxation. So MPI SPPI has a few different they call it bounders, so different formulations that come up with valid lower bounds. So any formulation that would come up with a valid lower bound, it's something you could use. The one we have is solving a Lagrangian relaxation of the problem, and so that gives you lower bounds. But of course, because we do have those binaries, those are not guaranteed to be tight. So that those, even though they're valid lower bounds, they may be below the optimal. So they're not guaranteed to be tied to the optimal solution, even if you run forever. So that's in part where the gap is coming from those lower bounds, not going all the way up, but also from as you find better and better solutions, exploring the search space is hard because you have those binaries and integer solutions. So that's where your upper bounds are coming from, is from just getting from the solution to the individual scenarios, mixing those in some way to obtain one feasible solution and test it. And once you have that test, you have one valid upper bound. I hope that answered the question.
And there are other journal articles about that, according to other members of the audience. Thank you so much, Tomas. We see there's some other virtual questions in the queue. Apologies to those folks. We'll have to reach out directly to Tomas for answers. We have to move on to our next speaker in the interest of time, but let's give Tomas one more round of applause.
Thank you.
Our next speaker will be Eknath Vittal from EPRI. And Eknath will be presenting on extreme weather impacts and considerations on the transmission planning process. Eknath, please.
Thanks. So the work I'll be presenting today is part of an ongoing initiative at EPRI called the Climate Resilience and Adaptation Initiative. What we're focused on today is how to address studying extreme weather scenarios in the transmission planning process. So transmission planning is usually a snapshot reliability assessment where a single representative hour is studied and addressed. Traditionally, this is an hour that is representative of high utilization of the entire system. So we have high levels of generation availability where we only consider the seasonal and maintenance outages that take place, and we represent an exceptional load demand condition. Next slide, please. FERC Order 896 and the ongoing development of the NERC TPL 8 standard has introduced a new planning process where we now have to capture an extreme heat or an extreme cold condition and complete the traditional reliability analysis. And traditional reliability analysis is on that traditional base case that I just described. We run lots and lots of contingency analysis. So we have different combinations of contingencies defined based on the protection that's in the system. So we have different representations of failure modes that occur for generators and transmission lines, transformers, and equipment connected to the bulk system. What we're now being asked to do through this FERC order and the upcoming standard is represent a stressed initial condition that now, instead of high utilization where generation is available across the entire system, we have to consider the potential impacts that the extreme temperature condition is going to have on the system. So are there going to be derates of fossil units due to extreme heat, unavailability of natural gas, as we saw earlier during these extreme cold events? And once you represent that generation unavailability in your system, you have a stressed initial case. The upcoming standard is going to require you to run P0, which is the base case, make sure that that is secure, and any deficiencies for P0 or P1 contingencies will require mandatory corrective actions to be implemented in your system. So next slide. What we're going to be focused on is how do we identify the base or that new base case condition, right? When we're considering an extreme temperature event, it is occurring over multiple days, over multiple hours. Which hour do you potentially select to form the basis for decision making that is going to result in significant potential investment in your system? If you are developing corrective action plans in response to generation unavailability, you want to make sure you're getting a representative case that will capture many of the conditions that you could experience over the entire span of that extreme temperature event. If you consider, for example, an extreme heat event, it makes a big difference if it's a 3-day heat wave or a 7-day heat wave, because how generation unavailability is going to be represented and how human behavior responds during that event is going to create significant potential impacts. Next slide, please. The basis for TPL 8 is going to be a set of benchmark extreme temperature events. So what we have here are 4 different heat wave events that we've captured from historical data that are representative of 1 in 50-year heat events that occur over different spatial and temporal considerations. Moving left to right, we have increasing intensity essentially in those heat waves, but they all have the same likelihood of occurrence. A and B are 10-day heat wave events that occur in A over the entire state, B over a single city. C and D are events that occur over 3 days over that same spatial dimension. which one do you choose to serve as the basis for your planning scenario? Because when you're doing reliability analysis, the effort and time that it takes to get a converged AC power flow case and run all of the contingency analysis is very computationally and labor intensive. You have to create representative contingencies, run all those representative contingencies, and identify what are the reliability upgrades that need to go into your system. Next slide, please. So how do we evaluate multi-period weather risks over multiple years of weather and climate data to ultimately select what should be the representative condition? So we've developed an efficient screening methodology. Next slide, please. That will allow you to basically identify what are the most significant extremes in your system in terms of energy availability, and then use another technique to basically find from those extremes, find what are the representative hours that you should be studying from a transmission planning perspective. So what we've done here is taken multiple historical weather years, passed them through different climate models and emission concentration scenarios across different locations in Texas to basically generate forward-looking temperature data that we correlate then back to the historical weather information that you need to basically determine the generation condition in your system. There's multiple different ways of doing this. The previous presenter presented a dynamic downscaling approach. We're using a quantile delta mapping approach here, where we're able to get the type of resolution that we need to be able to apply climate data to the power system. Next slide, please. The question then becomes, we have 710 weather years of information now. What are the extremes that we need to be studying? So we have a tool called the risk screening tool. It's going to be publicly available in the next few weeks. And it is a fast approximate method for identifying time periods of energy shortfall within the system. And these time periods then become the search space for determining the snapshot condition that we're going to run in the transmission planning study. How do we able to do this, right? We have the weather and climate data coming in from that quantile delta mapping perspective. We need to bring in asset vulnerability information to represent how we derate those generators in response to different weather and climate conditions that are going to be experienced during those 710 weather years. Next slide, please. So there's a three-step process that we have here. The first is taking all that climate data in there and passing it through to the asset vulnerabilities. Next slide, please. The asset vulnerabilities are represented as a set of heuristic rules that we worked with OEMs, different databases, GADs, TADS databases. We set these if-then rules based on the weather conditions that are present in the system. So, as a fairly basic example, you can look at the threshold for wind turbines if it's below 32 degrees and there's icing present, and there is no adaptation represented in the database for that particular wind generation site. There's a derate factor that's applied to that particular generator. We do this for the basic ones that we know, high cutoff wind speeds for wind turbines. Nuclear units, there's a temperature derate where the cooling efficiency of the unit is no longer available at 125 degrees Fahrenheit, so on and so forth, for all the different assets that you have present in your system. And what we do then is next slide, please. We pass it through this tool to identify these time periods and then use it to set the stage for different processes that take place in the power system planning chain, right? So we have capacity expansion, where if we're trying to determine what the forward-looking system looks like, we know which periods to test that capacity expansion model against. We can pick the most challenging weather years to run in RA or production cost analyses to get identification what should be there. We can construct extreme meteorological years versus a typical meteorological year. In this use case, what we're going to do is identify all of the hours that represent events of extreme energy shortfall risk, and use that as the search space that we use for determining which hours we should build in the power flow planning process. Next slide, please. You could link all those processes together to get a more informed view of it, or you could do what we do here. So we have a four-step process that we use in risk. So we have 26 weather stations that we have linked to the nearest generation units across the entire state. Next slide, please. For all the weather years and for all the hours within those weather years, we essentially estimate unavailable supply based on those heuristic rules. And we also scale the load based on the temperature consideration that is going to be present in that particular hour. Next slide, please. And then we essentially do a rolling window analysis across all of those weather years to identify what are the most stressful events where you might have the highest risk of energy shortfall. You can customize what you want to be screening for, whether it's a 7-day event, a 21-day event, a 10-day event, so on and so forth. And we basically rank the top of the list across those weather years. In the case of this case study, we had about 2,000 different individual events that all occurred over 21-day windows. Next slide, please. And then once you have all of those events, to start making sense of them, we apply some pretty basic clustering through k-means to group different types of events together, right? If you have a 21-day event that is occurring with high temperatures and low wind speeds, you'll create a cluster around those. If it's a cold event with significant precipitation, it'll create a cluster around those. So it's basically organizing the information that's represented in these extreme event conditions. Next slide, please. What we're able to do when we've projected this information forward is we get very high correlation to the historical events that have been captured, right? So we can see that the highest risk events for cold and heat correspond with some of the historical extremes that have been experienced in the past. This information is projected forward now, and we get high alignment with what has been experienced by the state during these periods. Next slide, please. How does this manifest as energy shortfall risk? So as we look over time, and depending on how you project your load, technologies, things can change. But what you're able to do is in the colored bars that you see there is you're looking at the potential energy availability in your system. So across all the different asset classes that you have in your system, how much of that is available at any given hour? And then we project that against the load, and what we identify are these periods where there's going to be energy shortfall in your system. And we essentially use those entire windows then as the search space for what we're going to do the transmission planning assessment on. Next slide, please. We can do this for both the extreme heat and the extreme cold conditions. This is a representative of a summer case where we have less generation availability due to the extreme heat condition, and we're projecting a shortfall falling between September 4th and September 5th in 2050. And we have this all mapped back to all of the historical years and the projected climate models that are used to create this information. Next slide, please. So how do we now go from all of this information to a single representative snapshot condition is the next challenge. So we've identified these periods of potential challenging operation. We use that as the search space for our next search of identifying which particular hour to use. Next slide, please. So we have about 93,000 hours that we have to search from those top 5 events. And we began to organize it based on available headroom and the generators that are present in the power flow case against the load that is accounting for weather in the system. And we can create an initial cluster based on the loading that is going to be represented in the system. And we see, we break it down into three conditions that represent a low load, a medium load, and a high load condition. And as you see, as you get higher loads in the system, there's less and less available headroom. And as we plan on building that transmission planning case, those medium and high load conditions would represent the highest stress conditions for an initial case. And as you run more contingency analysis on it, the potential for violations and significant impacts is much higher during those particular conditions. Next slide, please. So how do we identify these snapshot conditions? So a traditional planning approach is a non-exhaustive search. We presume, based on historical experience, the most challenging case is going to be those edge cases with high demand. We assume that high level of availability from our generating units, and we essentially created worst case scenarios by saying, I'm studying my summer peak or my winter peak, everything else is a shoulder. If I can meet in between those two boundary conditions, I should have high levels of reliability across my system. Now what we're seeing with extreme weather impacts is a need for a more robust approach to identify what those initial conditions should be. It's likely infeasible to study 93,000 hours as transmission planning reliability assessments. So we need to reduce the search space to a more reasonable level of cases that planners can study. So for those hours identified by the risk tool, we want to get to a point where we have representative hours that we can use and say that we've captured sufficient amount of variability across all of those extreme conditions. If you study these 5 cases versus these, 5,000 cases. Next slide, please. Again, we have another tool that is leveraging principal component analysis and clustering techniques to basically pre-process the data, which is a very important stage in this process. So we want to understand what are the key features that are present in a particular data set to basically understand and normalize all that information. We use principal component analysis then to reduce the number of features that we need to study. We identify what the key features are that capture important relationships between variability and uncertainty. We classify the data then based on similarity and k-means, and then for each cluster that we develop, we apply sampling methodologies to make sure that we're picking a robust set of hours from those particular clusters to capture enough variability and get to a point where you can say, if you study these dozen cases, you have 95% of the variability of the extreme conditions that we've already screened and captured, and you should have a pretty robust and reasonable representation for making transmission planning decisions on. Next slide, please. So what we did in this particular case is we looked at the high and medium load hours from that initial clustering. We first organized the regional generation unavailability due to weather. There was a regional representation of load variability, and that's how we developed the features that we started doing the principal component analysis and clustering around. From that clustering analysis, what we see are 5 distinct power flow patterns emerging across those times. So around those 5 clusters, we selected the highest load hours to focus on those periods of high transmission stress. What we had time to do was build 2, or actually 3, a base case of that future year where you're around a typical planning scenario, and then 2 additional snapshots representative of the 2 of the patterns that you saw in step 3. Next slide, please. So what we have is a baseline case where this is built on the high utilization principle. And then we have two cases where we have a similar load condition, but with a very different generation pattern in the system. And another case where it's a lower load set point, but it again has a different condition. Both are representative of extreme heat conditions. The question then becomes, which one is the new worst case that you need to study and build around? That question is really answered by the reliability analysis that you complete itself. Next slide, please. What we see are very different dispatch patterns emerging, and what we found in doing the reliability analysis is you end up building many more miles of lines compared to the base case consideration as a function of where you have generation availability to supply the load in your system. Right. And this is functionally what TPL8 is asking you to now consider and do. And do it beyond just your operating footprint as well. So it is a standard that is going to require regional coordination because the weather event in this case, it was easy because Texas is electrically isolated from the rest of the system. So we're not looking at interregional transmission as a potential solution. For other more interconnected systems, the climate event or the weather event isn't just going to sit on your balancing area or your operating footprint. It is going to impact your neighbor's ability to import generation into the, or your ability to import generation from your neighbor or export to another neighbor. So development of that base case that's representative of that weather condition is going to be a coordinated effort. TPL8 is designed to facilitate that coordination, and we'll have to take a process where similar to this, where you look at a weather condition and translate it to a set of energy scenarios that you ultimately study and make investment decisions on. So I hope this is a first step in a broader process where you can capture regional variability, uncertainty around extremes and represent them through asset vulnerability and ultimately down into the transmission planning space. So that's all I have. And next slide, I think I have one more slide just summarizing things. So we've only really captured generator derates here. There's a step beyond this process that TPL8 is going to ask you to consider as well. It's difficult to consider it deterministically. It's the actual unavailability of the unit, especially as you get to plan a single unit, a single snapshot around that. Our preferred approach has been to address it through a more robust integrated planning process where we use resource adequacy or production cost modeling to create the draws that are representative of those particular outages. If that capability and process isn't available to all planning entities that are going to be required to adhere to TPL8. So there's more deterministic processes that we're looking at that try to represent a robust outage picture for generators in this single snapshot. Again, if you're making corrective action decisions based on a particular fuel type being unavailable, the investment decisions and corrective action plan that come out of that are specific to that particular outage. So being able to capture something statistically robust and accounting for how coincident weather conditions can drive those are some of the future research that we're looking at here. Again, happy to take any questions. So.
Thank you, Eknath. We have about 5 minutes for questions. Any questions from our room?
JP Watson, Lawrence Livermore. I was curious if you could say more about the sorry, that's echoes annoying. About the release, like what are you releasing exactly? The tools, the data sets, or you just?
The tool itself will be released. The risk screening tool will be released. It'll be a Python-based tool that will be hosted online in a public Git repository, essentially. And what that tool has is the scripts that allow for the screening, but then also examples of the asset vulnerability databases. And you can, the climate data you'll have to develop for the particular region that is there. So there'll be an example case that the Texas example will be fully released along with it. But part of the challenge around the climate data, we're also addressing through Nyiredy, where we're pointing you to the right databases for your regions and where you can make that data available. We're building a robust asset vulnerability like repository, I guess, online as well, where you can get more specific regional representation of, a gas plant in Minnesota is hardened differently than a gas plant in Tennessee. So being able to capture those differences in how you represent asset vulnerabilities is information that we will make available and provide for everybody as well.
Do we have any questions from the virtual audience? Any more questions from the physical audience? Yes.
Well, Will Frazier from Ncord. Is the tool a series of scripts that needs to be run manually, or is there a possibility to make that sort of a pipeline where there's a set of inputs that you would need? And
You can certainly do that, right? It's a standalone tool where it'll be packaged as there'll be essentially a batch file that will allow you to run everything, but the intent is to allow for development and customization as needed, because I think the requirements of TPL8 and the need for something like this to exist aren't there yet commercially. So our intent is to make it available and provide as much of it as we can. So you could tie it into the front end of many different processes, not just transmission planning. As I've mentioned here, it feeds into either, we've had inquiries into short-term forecasting, how you could use it there. What it does is, in absence of a supercomputer that allows you to run hundreds of scenarios, it gives you those focus periods of extreme event challenge, and you can use it to do more dedicated assessments and testing and validation on some investment decisions that you're going to have using existing tools and processes.
Great, thank you.
One other thing that I will mention is that it also allows you to build in the adaptation decision that you want to take. So under an extreme heat condition, if you derate natural gas turbines, right, by a certain percentage of the units, you decide to invest in inlet air chillers as the adaptation decision. So you can go in and modify essentially the capacity curve for that particular unit. And you'll see that shift in when your unavailability risk is going to change in the system.
Thank you. Do we have any more questions?
This is Bo from Cornell. I have a question about the historical weather data and when to use historical weather data or when to use climate forecast. You mentioned in your slide like some of the 2050 extreme events are well captured in some of the historical events. So can you please comment on can we use some reanalysis the weather data to replace some of the climate data?
So this is essentially real analysis weather data. So we use the ERA5 data set and we project it forward through different climate models and emission scenarios, right? So what the reanalysis data allows us to do is correlate the other important variables that represent the internal variability of weather and have significant impacts on power systems to a temperature condition. That temperature condition is what's projected forward through the climate models. So you can understand what that temperature change is going to look like in 2050, but still have some synchronicity to the internal weather variability. Climate models themselves are not robust at capturing that internal variability. They're predicated on the emissions forcings and anthropogenic changes that are happening. So being able to have something that like outside of dynamic downscaling that represents a efficient methodology to capture climate and the weather variables that impact power systems. This is the approach we chose. You can use a more comprehensive approach if you wanted as well that involves dynamic downscaling.
All right, maybe time for one last question. Or
a hurricane and then a heat dump.
the question was, you would call a hurricane and a heat dump?
You could. Do you want to train your capacity expansion model to be robust to both of them? Yeah, you could, right? Like, and I mean, we just saw it happen now, right? So as long as that weather pattern, like one of the things that we're working to build is the transmission vulnerabilities in the system as well. Right now, it's basically generation outage and generation risk. So if you want to capture a hurricane, you want to be able to represent the transmission outages as well. It's a little bit trickier, but we're working toward it as well.
Thank you. One more round of applause for Eknath. All right, our final speaker for this session will be Miguel Ortega-Vazquez. And Miguel is from EPRI. He will be presenting on dynamic assessment and determination of contingency reserves. And Miguel will present virtually. Hi, Miguel. Miguel, we can't hear you if you're talking. Can you please try unmuting or check your audio settings? Miguel, we still can't hear you. Can you hear us? Still no sound, unfortunately.
It's not on our end, Alex.
Got it, thanks. Still no sound, sorry.
What about now? No? I'm gonna keep speaking. Work? No?
It's good. The volume keeps changing a lot. Can you try talking some more? That we can see that you're talking, but the volume keeps changing a lot. You keep cutting in and out. Is there another device you can use?
How about this one?
That sounds excellent. Thank you. Please go ahead.
Yeah, sorry about that. Yeah, no, I have a number of things here, and I just have to choose from the software which one is the one that is to be used. I apologize for that. Thank you very much for the previous presentation as well, and from the previous presentations that have been letting the work a little bit to change gears into a little bit of operation. Where the focus has been here mostly on planning. And the question that I will be trying to address here is, what do you do in actual operations when you have extreme weather conditions? And particularly, we'll be focusing on how to parameterize the reserves that you need to carry under extreme weather conditions to respond to unforeseen events, particularly in the domain of forced outage of power system assets. So in the next slide, I just have a little bit of introduction. I just say that, operating plans are typically drawn from day ahead. And in the day ahead, what you are trying to do is to allocate sufficient recurs so that whatever deviation that happens from forecast, you have sufficient headroom and foot room to accommodate it. And there are many different alternatives in the operation research space that deal with stochastic optimization, robust optimization, chance constraints, and all these kind of things. But what system operators actually use is, a plain constraints to allocate a given amount of headroom and foot room, and they need to determine that the right-hand side of those constraints to make sure that that headroom that they are allocating is sufficient to accommodate all those deviations. One of the and they categorize this headroom and foot room into different rubrics. They have regulating reserves, flexibility reserves. They also have flexible ramping products, and they also have contingency reserves. And this is on this last item is that we're going to be elaborating a little bit more. It's the contingencies that we want to parameterize. So NERC also has some reliability standards that they need to be met. In particular, the VAL 002 that says that system operators need to carry at least an amount of reserve sufficient to respond to the outage of the largest online resource. So that's the N-1 criterion. And this approach may work well when you have some deterministic or when you have normal conditions in which the largest in feed is sufficient protection. However, this kind of rules of thumb disregard a number of things. First of all, this disregard the likelihood of the contingency. So they really do not consider how likely that contingency is to happen. It also it doesn't take into account the impact of that the contingency will have on the energy redistribution in the system, and it also disregard the weather conditions that you may be facing in that particular period of time. So in particular, you may have normal operating conditions in which everything goes as planned, and if a contingency happened, you were prepared for that. But you also could have extreme weather conditions, whether it's extreme heat or whether it's extreme cold, and under those specific conditions, the failure rate of your generation and transmission assets changes, and therefore the likelihood of a contingency changes, and even you cannot potentially disregard higher order contingencies, not just the N-1. So this is what we want to have a method to be preparing the system against. So in the next slide, I'm just giving the kind of elevator pitch of what we are trying to do and how are we going to do it. So we need to that we need to revisit the methods that we have to parameterize contingency reserve requirements. And our objective is that we want to ensure security under all possible operating conditions, not just normal operating conditions, but also extreme weather conditions. Why? Well, because extreme weather conditions are becoming more frequent in power systems. There's a large body of evidence that these conditions increase the likelihood of outages of power system assets. And how are we going to do it? Well, the way that we are going to do it is by using different metrics. In particular, we are going to be using risk, and risk is nothing else but the expectation of not having sufficient reserves. And by being an expectations, it takes into account probability and also takes into account the magnitude of the potential events. And who should be interested in this kind of approaches? Well, any power system stakeholders that are in charge of designing or determining operating plans, or even planning of the system, in order to ensure that the system will be doing what it's supposed to be doing under these cases. So in the next slide, I'm just presenting some a presentation that was made here in this conference as well, I think, in which they are just summarizing what happened in the winter storm Elliott in 2022, and they were just mentioning that there are a number of unplanned generation outages that increase beyond normal levels, and they made a number of recommendations of what to do in order to take into account these kind of things. You know, they have to revisit reliability standards, they have to improve load forecasting. They are proposing to include new processes to assess system risk, and then, you know, having regional reliability assessments, a number of things. So one solution that we are proposing here is just to have a risk-based approach to dynamically dimension reserve capacity under normal and especially under extreme weather conditions. Now, again, in the next slide, I'm just summarizing the various factors. If we can move to that next slide, that should be taken into account when we are parameterizing the reserves. We have to take into account the reliability standards that apply to our particular system. We have to take into account which units are available. Before we were mentioning that, you know, there's particular periods of time we have seasonal and maintenance outages, so not all generation is going to be available. And on top of that, we are going to be synchronizing just a subset in order to meet the expected demand. So we have to take into account generation, scheduling, and dispatch. We have to take into account as well the reliability of the various assets that we have there, like you know, the failure rate of generators and transmission. We have to take into account the system demand that needs to be served, the production from wind and solar, the weather conditions, whether they are normal conditions or extreme weather conditions, and system topology as well. With that, we will be determining the amount of reserve that we should carry, how much reserve we should put whether it's a spinning or a standby, how much reserve should be available and to be ready to be deployed. When do we need that reserve, at which particular hour of time during the planning horizon, the operating planning horizon? From which resources should that reserve come from? Because different resources have different reliability, and then different resources are also located in different parts of the grid. And we also have to take into account where in the grid are we going to locate that reserve, such that in post-contingency states, that reserve is still deliverable, and that is not going to be behind a congested transmission corridor. Okay, so in the next slide, I'm just showing one of the tool that we develop in order to do this in a programmatic manner, in a simple manner. We call it Dynadecker. It's a Dynadecker. The name of the tool stands for Dynamic Assessment and Determination of Contingency Reserves. And this is a tool that, you know, consumes system data, the data that it needs. It's typical data for a production cost model process, a generation, a scheduling model, plus the reliability data of the system, plus the extreme weather curves that I will get into in a few minutes. This is a tool that has been designed to be applicable for different regions, whether it's, you know, ISOs, balancing authorities, TSOs, etc. So you can customize it and you know, to fit specifically the product that you are trying to dimension in terms of time, magnitude, resources, etc. So this is just how the tool looks like. And then in the next slide, I'm just showing where that this tool fits in the whole ecosystem of from planning to actual operations. typically we start or planning assessment in the box number 1, in which we have coordinated expansion planning, as some previous presenters were talking about, in which we look at investment in generation, transmission, and storage, emerging technologies as well there, and we take into account uncertainty, long-term uncertainty there. We typically start with some planning reserves. Then after that, we do some resource adequacy studies in order to make sure that the system is adequate in terms of energy, flexibility, etc. Then we do some data analysis and selection similar a little bit to the PCA approach that Eknath mentioned earlier, in which you look at periods of potential stress to the system. And in those days, what we do is just to make that assessment more rigorous. We apply this system tool that we use to parameterize reserves, which is Dynador and Dynadecker. Dynador focuses on continuous events like in products like, for instance, regulating reserve, flexibility reserves, ramping products, and Dynadecker, which focuses on contingency reserves, as I was talking earlier. From that, we can just make further studies to the system, whether, to assess flexibility or to assess whether it has sufficient primary frequency response, etc. And if not, we can reparameterize these studies with the issue on planning reserves or operating reserves to ensure that there is going to be some coordination across all the different stages from planning to operation. So in the next slide, I'm just showing the various 5 boxes. So the various processes that are required to parameterize contingency reserves. On the first box is just consuming data. So we just take data from our system, that it takes into account all the variable cost, the startup cost, minimum stable generation, capacity of the generating assets, minimum up and down times, ramps, etc., the different reserve products that we have to enforce. And we also take into account reliability data like the mean time to failure of the generating units and transmission, whether there are failures to synchronize, and the weather conditions, whether they are normal weather conditions or extreme weather conditions. The next box number 2 there, it runs a generation scheduling. This we can use a commercial tool or proprietary generation scaling tools. We can use like Plexus or PSO or any other tool that essentially we are minimizing the operating cost of the system, subject to all the technical constraints of the generating assets and transmission, and then we will be determining which units are synchronized and the power at which they will be dispatched. From there, we do, in the third box, a risk calculation, in which essentially we build the outage distribution the possible, the probability distribution of the various outages that we may have. So we compute the probability of any given outage and the magnitude of that outage. And then we also determine, or what we do is that we take the probability and the damage to the system, and then we just multiply those quantities and sum them up, and that's what we call risk, which is just essentially the expectation of the cases in which we will not have sufficient reserves to maintain power balance after a contingency materializes. So with that, we go to box number 4, in which we can create the risk profile over the horizon that we are studying. For instance, in this case, we have 1 day that we are exploring. That's the green light that we have there. And we also have a risk tolerance, which is that dashed line there. And we can see that during peak net demand periods, the system risk, the expected system risk, is greater than the risk tolerance that we propose. So that's the area in red. So under those specific periods, then we have to increase the contingency reserves that we are carrying in our system if we want to bring the system risk to a level that we are comfortable with. So All the other periods are obviously below the risk ceiling, so they are okay. So in those specific periods in which the system risk is greater than the risk ceiling, we engage into a process to update the reserve requirements. It's a gradient search method in which we increase the amount of reserve linearly with respect to some calculations that we make in the background there. And then with those updated reserve requirements, we compute again the system risk. And if the risk is still greater than the ceiling, we update the reserve requirements once again. And if the risk is below the risk ceiling, then we call it a day, and we say that the operating reserves that we are obtaining for that iterative process are the ones that we have to enforce in order to ensure that the system risk is going to be at a level that we deem acceptable. So in the next slide, I just want to emphasize what is risk, because
Miguel, sorry for interrupting.
Yeah.
Just to note, you have about 5 minutes left.
Oh yeah, thank you. So just quickly, just to mention what is risk, because typically we do system operations with probability ceilings, and again, risk is not a probability alone. It has to take into account the magnitude of the event as well. So it's a long-term average or of the contingency reserve shortages. So in the next slide, I think no, we can skip the next two slides. And then there's another important part, which is the extreme weather, and how do we include the extreme weather. So what we do is we base this model in the manuscript, in the paper that it's on the bottom, reference in the bottom there, in which we use a Markovian model that takes into account a number of factors to make transitions from the available to the unavailable state, and they are based on different curves that are obtained to a particular region, that essentially at the end, what we are trying to do is to generate a curve that tell us what's the failure rate as a function of the temperature in the system. So if we have very low temperatures, we will see that the failure rate of the assets increases. And if we have high temperatures, a similar effect will have, in which we have the failure rate increasing. And from normal operating conditions, normal temperature thresholds, the failure rate should be very close to what we have in our GATS and DATS databases. So that's essentially the model that we are building using this process. So in the next slide, we applied just to get some numerical results. We applied this method to we have applied to some different systems, and in order to share these results, we are using here the RTS ELMC system, which has 73 units and a total thermal capacity of 8 gigawatts. The data for this system it's available in that link in GitHub, and also it's detailed in that manuscript and the bottom. So when we just run this model, in the next slide, we can see the generation scheduling that we get for the typical case in which we are using just the N-1. So nothing out of the ordinary here. So just to get the generation scheduling and dispatch. And in the next slide, we compute the risk profile for that particular generation scheduling. We can see that there are a number of periods in red in which the risk is greater than the risk ceiling. So what we do is that we engage in the iterative process that I was mentioning earlier, and we can see in the next slide how that iterative process takes place. We go from that risk that was around 58, and under each iteration, we can see that the risk, and that's on the figure on the center and the bottom, we can see that the risk profile of the system is becoming lower and lower. Finally, when we get to the risk profile in blue, in which the expected risk of the system is below at all periods to the risk ceiling that we are enforcing. And the byproduct of that is the reserve requirements that we have on the bottom right, in which each iteration, they are larger and larger, but only on those specific periods in which we have, system risk larger than the ceiling. So that's in a nutshell, that's the gist of this approach. We are just essentially revisiting reserves on the risky operating conditions until we bring the system to a comfortable level. And in the next slide, we can see that if we consider that was under normal conditions, and if we consider extreme weather conditions, the failure rates of the assets increase, and therefore the system risk exposure, which is on the bottom right, also increases. So we can compare that to the 94.8 that we have in that figure against the 58.9 that we had under normal weather conditions. Again, we engage in our iterative approach, and we bring that risk to an acceptable level. But obviously, on the figure on the far right, on the top, we can see that the revisited reserve requirements are greater than those that we should revisit under normal conditions, because the failure rate of the generating units, it's greater under extreme weather conditions. So that's the general gist of this approach. Just finally, on the next slide, just to summarize, is, system operators uses rule of thumb to parameterize contingency reserves. They are practical, but they disregard a number of things. And what we are trying to do in this model is to take into account all these other externalities as well, in order to include them in the reserve determination process, so that we compute contingency reserve requirements that will give us peace of mind that the system will be reliable, even if different unforeseen events materialize. So that's my presentation. Thank you.
Thank you, Miguel. Do we have any questions from our in-person audience?
Hi, this is Kanchan from New York ISO. I have two questions. The first is, what do you envision the time frame of such an analysis would be? Like, would it be seasonal determination of reserve requirement, or would it be more like kind of day ahead? And the second question was, I think you talked about like the transmission constraints consideration in the modeling. So when you do this assessment, is it like over a balancing area period, or is it more locational requirement as well? Thank you.
Yeah, thank you for the question. So absolutely. So this tool has been designed to develop day ahead plans, but obviously you can use over a season and then determine what are the, with other heuristics, what would be the seasonal reserve requirements that you need to enforce over that particular period of time. But the tool is flexible enough to determine day ahead operating plans. So that's the main idea here. In terms of constraints, the model, I didn't get into the details of the model that determines locational requirements in order to ensure a post-contingency deliverability, but that model is nodal. So it will tell you what are the nodal reserve requirements that you should have at each part of the system in order to ensure that those reserves are going to be deliverable in post-contingencies. So does that help?
Yeah, that does. So follow up on that for the nodal determination, you mean?
Step forward just a bit.
Okay.
Perfect, thank you, sorry.
So for the nodal determination, is it like based on the balancing, the different reserve areas that a system operator would have, or is it even more granular than that?
Yeah, it's the whole system. You can use it, the balancing area. You can use the larger system. As long as you have the information, you can consume it there. So yeah, does that help?
Yeah, that helps. Thanks.
Any other questions from the in-person audience? we have any virtual questions? Going once, going twice? All right, well, thank you, everyone. Let's give Miguel another round of applause.
Thank you.
All right, thanks again, everyone. That concludes our session WB1. We'll now take an hour break for lunch. Please come back to either this room or the commission meeting room at 12:30 for the next sessions. Thank you. Any other announcements? Hi, everyone. Welcome back to the conference, to session WB2. I'm just about to get started, waiting for a few folks to trickle in. Before we get started, I just want to shout out a quick reminder that while we do love discussing market power design and power markets design and power market software, we'd like to remind everybody to avoid speaking on the merits of any proposals that are pending before the commission currently. And we'll try and flag those if we hear any discussion that seems to be veering in that territory. Due to commission rules, we're not allowed to talk about those kinds of things. With that, I'd like to introduce our first speaker for this session. That's John Condren from PowerGEM. John will be speaking on PowerGEM Terra worst cluster TrLim analysis for system-wide bus injection capability and heat map to address FERC Order 2023. John, please. Thank you.
Thank you. I'm John Condren, and Boris Geeson is here today with me from PowerGEM. Sungwon An also worked on this presentation. He's from PowerGEM. We're going to be talking today about PowerGEM's Terra software and a new feature we have added recently that's called worst cluster TrLim analysis, and also we have a new heat map capability, both added to address the FERC Order 2023 requirements. Next slide. So first, we're going to start out doing an overview of the FERC Order requirements. We'll take a look at some of the PowerGEM Terra legacy solutions that people have been using up until worst cluster TrLim was developed for doing the injection capability calculations for every bus in their region or a subset of buses of interest. And then we'll go ahead and look at the new worst cluster TrLim approach, and then show you what the heat map looks like. Next slide. The FERC Order 2023 requirement is for posting on a public website what is the injection capability at each station in your system, each bus in your system, we'll call it that. And you're supposed to show where it is, how much is available at that location, what are the most limiting constraints that are affected by injecting at that location. And so one of the things that the order doesn't talk about is how do you do that calculation of injection capability. Doesn't tell you all what you should show on the map, like how much detail should you show? Should you show where the monitored facilities that are impacted? Should you show where those are? Should you show what the contingency names are? How far should people be able to zoom in to see where these locations are? That's not mentioned. So that would be up to the transmission providers to decide, and then of course who will host this heat map. Next slide. So that's where we come in here as far as talking about how do you compute that injection capability at every bus. The thing that they didn't mention, that how you're supposed to do it. We have some potential ways here that we're going to be talking about today. Just a little bit about the PowerGEM Terra application. It is widely used in North America for steady state analysis. We have over 230 companies using it as of this year. All the ISOs have licenses, site licenses, a lot of transmission owners, FERC, NERC, all licensed Terra. And a lot of developers also license Terra for looking at where they want to site their new projects. Terra can help them do that. And that's where the transfer limit analysis comes in. That's one of our most popular applications, especially among the developers who are looking for, as I inject at a certain location, what are all the MonCon limits that are going to pop up? So we call that a TrLim analysis. It's also can be called FCITC, which stands for First Contingency Incremental Transfer Capability. So if I use these terms, FCITC, transfer limit analysis, we're going to be calling those the same thing here. I'll be using that FCITC term a lot here. But we have a tool in Terra for doing this. It's often used for the bus hosting analysis, running the FCITC on the one bus of interest or on multiple buses of interest. I'm injecting there and then withdrawing at a whole set of other buses, maybe all the existing generation. So we've had a lot of new features there over the last few years. We got AC verification for that, very high performance. We can even do automatic evaluation of all the line taps. If you give us a set of lines in the system, you want to look at tapping, we'll tell you injection, the FCITC values for each of the line taps. And then a second one that's really popular is the generation deliverability tools in Terra. GenDeliv is a short for that. We have PJM, MISO, and KISO add-ons that can be purchased for Terra that are endorsed and were co-funded at least by the ISOs for running their gen deliverability tests that are then used for evaluating the queues of generation projects that are coming in. And so those are all built into Terra. That includes a flow gate screening application to identify which MonCons can be impacted by redispatch. We'll talk about that a little bit more later. But this is used by a lot of our customers, transmission owners and developers and consulting companies. So we have the two legacy applications here, FCITC, TrLim, traditional FCITC approach. We have the gen deliverability approach. And then now what we're adding is a third one, which is the worst cluster TrLim. That's the new one developed late last year. We released that. And it kind of combines these two things, the FCITC and the generation deliverability. As compared to FCITC, it's looking at many other dispatches other than your base dispatch. So that's better than FCITC. And then worst cluster as compared to GenDeliv it is looking at all those potential dispatches that could cause overloads, but it's much easier to set up than a typical ISO-based GenDeliv, and it's not tied down to their custom rules. And it is focused on prospecting mode. By prospecting mode, I mean, that's where a developer wants to go out and look for locations to build. Can you have a bulk analysis mode that evaluates a whole bunch of locations in one shot? And that's the idea here is it not just for the FERC order analysis, it's also for developers looking for prospective locations. Next slide. Now your traditional FCITC or legacy FCITC application, when it does a test of one particular bus, in this example, you see the one in the upper left-hand corner, you're testing injection capability at that location. Right now, there's two other projects in the case that are located right nearby, proposal number 1 and proposal number 2. They came in as offline in your starting case. And so the injection capability here would be the rating of this line. You could put up to 150 megawatts of generation at that test bus you're interested in, assuming that the other two aren't running. But as soon as you turn on those other two units, one at 100, one at 25, now you eat up 125 of that line's capacity, and you got 25 left for you. And so this is the situation that we're trying to find these situations by running the new worst cluster TrLim. GenDeliv already does find these situations, our existing PJM ISO add-on GenDeliv tools. But the FCITC would not find this because it only takes the base case dispatch, whatever you start with, and injects on top of that base case dispatch. In this case, you would get an answer of 150 when really, if you wanted to go with a true network firm deliverable capacity value should have been 25. Next slide. And so therefore, the problem is we saw those two Q generators. If you were trying to turn on every Q generator in your entire case, or that was in the queue, every generator in the queue, and turn that on in your case so you don't miss any problems, well, you just turned on more megawatts than you have load potentially, or it could be, it just doesn't solve. It's just a huge amount of generation. As we see in this slide here, we took that from the presentation cited at the bottom here. Over the last 20 years or so, like hundreds of gigawatts of new queue projects have been put into the queue. Now, not a lot of those go forward, of course. And so you got all these new projects coming in, huge amount of gigawatts of generation. How do you evaluate all the potential dispatch problems that would be associated with adding all these new queue projects? Next slide. And so if you're running FCITC and you had that huge interconnection queue, how would you do an FCITC or injection capability calculation at one particular bus? Well, you have to create a load flow model with a starting point dispatch in it. And as I just said, you turn on all those thousands of Q megawatt generators, you try to do that, your case probably wouldn't even solve. Some regions, though, handle this by, they break their region into sub-regions. So you have a west and a north and a south. And they'll build a case for each one of those three regions, for example, turning on only the Q generation in those regions. But the problem with that is now that case even has problem solving. And then what about the generators in that region that are on the border? Maybe the border ones affect the north part, border ones of the west affect the north, and similarly the north affects the west. So that's not a perfect approach either. And then on top of that, if you got cases like that the ISO is responsible for building and maintaining those cases, how are developers supposed to try to reproduce this procedure? Because they'd like to go in and do a test before they submit their project to get some idea of what the answer is going to be when they submit their application. Next slide. And so with generation deliverability, our generation deliverability tools, the idea with those is that you use a single case, and a lot of times they keep their existing fleet of units that are currently in service, keep those online and dispatched. But you turn the Q generators, they're all offline in the case. So it solves just like normal. And then you evaluate issues caused by small clusters of several generators running at the same time. And that way you can identify bottle generation issues. We also have capability of looking at transmission service requests. So if you want to transfer from one area outside to inside the region, those can be handled too with deliverability. And so deliverability, GenDeliv, is less dependent on your initial case dispatch. The results you get out of it are less dependent on initial case dispatch. And Terra's new worst cluster TrLim is like those GenDeliv methods, but it's generic. It's not bound by the ISO rules, even though it is user configurable, some of the rules. Right? Now, the problem with our existing GenDeliv tool, you're going to say, well, why not use those for computing injection capability at a whole bunch of buses? Well, we just use the ones we have. Well, they're not designed right now for evaluating capability at a whole bunch of user-defined interested locations. Their primary usage is to evaluate a set queue of new projects where you know where they are, you know how big they are, and you're trying to determine how much of an overload does this given project cause. That's the current focus of the GenDeliv tools. But it's not what the FERC order is needing and not what developers are needing. They want to do this prospecting mode where they're searching for how much they can put in different places and evaluate a whole host of locations at once. Existing GenDeliv cannot do this. Right. And then the problem with the legacy FCITC is a lot of those or a lot of people try to use that to evaluate injection capability, but it, again, as we just saw in that diagram, is dependent, the results of that are dependent on the initial case dispatch. So what we want is to be able to run FCITC type injection capability. We want to take care of every possible bad dispatch that could occur, get that capacity, firm capacity, deliverability number for every bus. And so that's what worst cluster TrLim was designed to do. It's combine that deliverability and those FCITC features. Next slide. From the deliverability perspective, worst cluster TrLim, you'll pull in a single case, but it will evaluate many worst case dispatches. Your queue projects, you don't have to turn them on and solve this case with thousands and thousands of new megawatts. You just leave them offline, not running. They're in the case, but they're just offline. And then it'll use one of our tools that we have built into Terra, which is called flow gate screening, to identify all those possible dispatches that could cause issues. Next slide. Worst cluster TrLim will find this worst cluster of generators. We're going to test each MonCon, each modern element for each contingency, and find a cluster of generators that pushes the flow of that MonCon higher. So that will be a cluster of generators that's based on the defects of each generator on the MonCon that you're testing. And so when you apply that new worst cluster dispatch, it causes a higher flow in the MonCon and therefore a lower FCITC injection number if you're evaluating a bus that's near that MonCon. Slide, please. And then worst cluster TrLim also has a prospecting mode built in. Unlike Gen to Live, it's more like FCITC, our FCITC tool. It has a prospecting mode built in, so you can evaluate this huge number of buses. And remember, we're doing thermal only evaluation here, so you can use linear redispatch screening methods, DFACs, LDFs can be involved. Evaluate millions of MonCon pairs and thousands of test buses, and it just runs in minutes for many real world scenarios. And of course, you run the entire MISO or PGM footprint, that would take longer, but we're not talking about days here. We're talking about, hours, a couple hours maybe. And then the Terra Flowgate screening engine is what's behind worst cluster TrLim. It uses, like I said, LDFs and distribution factors to find which possible MonCon pairs could be overloaded given redispatch that could occur. And so if you have a 10,000 mons and 10,000 cons, you get 100 million combinations there we're testing, 5,000 generators, let's say. So we're looking at different dispatches among those generators and all 100 million MonCons and identifying all N-1 constraints that could be overloaded under all combinations of dispatch. You get like 10,000 flow gates out of that. Now, for a given generator, a bus that you're testing, there wouldn't be a lot that would be affected, maybe 10 to 100 of those, but because we use a distribution factor cutoff on the flow gates. Next slide. Now, Flowgate screening actually is a standalone app in itself. You could run that separately from the worst cluster TrLim analysis and just get a list of flow gates of interest that you may feed into other Terra reliability analysis, market coordination tools, or interregional coordination tools, and then market and production cost software like the PowerGEM probe software. Now, the second requirement for the FERC order was to show those injection capability results on an actual map with some colors there to show where the best locations are for building a project, how much is available at each location. You can see some links here on this slide that you can go visit for our particular implementation of that. We do offer a web application that can be hosted by the customer for showing those injection capability values on a map. And it also shows not just the one number, it also shows you the constraints that are impacted, and it can show you competing generators for each candidate bus that are all vying to inject and cause an overload together on the given MonCon pair. Next slide, please. There's a picture of it. You have the injection capability a table on the left side. So when you click one of those, it'll navigate to the location on the map. But there in the middle part, that's where you see the MonCons, the constraints that are impacted by a selected bus, injecting at that bus. And then there at the very bottom right corner is something that we've added that provides this additional level of information, which is for the selected MonCon, which generators affect the flow of that MonCon. And it shows you all the generators there and their defects on that constraint. Right. So the web application, it's very easy to deploy. It doesn't require a backend database, just a single page app requiring minimal setup. You'll just upload your results file that you got from running Terra into that folder with your web app. And now the one I just showed you in that picture was what we sometimes call a pro version that shows those worst cluster harmers for each MonCon. That's not required in the FERC order. You may just instead to do that, deploy a light version, which doesn't show those. It's the same information except for those worst cluster harmers are not shown. Right. So what we've gone over today is the new Terra worst cluster TrLim provides a prospecting mode for developers or for transmission owners. It provides a way to get show injection capability at every bus in your system. Can be used by either type of entity. And then we've also shown our Heatmap component, a web application, which by the way, I may have forgot to mention, we have a desktop application version of that too. So that's available for running, not just posting on a website, but every engineer could have their own copy of the Heatmap application running on their computer. And then a big part of that is we show those competing generators. Okay. Yep.
Do we have any questions from our in-person audience? Do we have any questions from the virtual participants? None so far? Okay, going once, going twice. All right, another round of applause for John. Thank you. Before I welcome our next speaker, I'd just like to give a note to all presenters who are in person that when you're queuing for your next slide, please speak into the microphone. The queue goes to our webinar manager, who is the true controller of the slides. I know we look like we are masterful over here, but we are actually not controlling the slides. The guy behind the glass, the one-way glass, Levon, who's doing a great job keeping us on track. And so when you're giving your next slide cue, just make sure it goes in here. And then with that said, I'd like to welcome our next presenter, who is Swaroop Guggilam from EPRI. Swaroop will be presenting on unlocking grid potential, holistic evaluation of transmission hosting capacity. Is Swaroop in the room?
I am virtually presenting.
Oh, great. Okay. Sorry, Swaroop. I was mistaken about that. Please take it away.
No, good. I hope you guys can hear me clearly.
Yes, you sound excellent. Thank you.
Awesome. Thanks. Thanks, Alex. And want to thank FERC for giving this opportunity to present. I think John's presentation kind of lays the foundation for my presentation, as now you got familiar with the hosting capacity itself, also the FERC order 2023. Next slide, please. So I'll be talking about three things, or mainly focused on the hosting capacity tool, but we also did a recent industry survey. So I'll talk a little bit about that. And then most of the time focused on the hosting capacity tool, we have at EPRI kind of determining that hosting meter, what we say, at each node, the maximum injection you can do, and then discuss what's next. Next slide, please. So we divide kind of the industry needs into 4 different areas. And the first aspect for us to learn was where the industry is at right now. So we wanted to do a survey. We kind of reached out to a lot of members and utilities to know where they are in respect to come for meeting their FERC Order 2023 compliance. So I'll talk a bit more on that. The second aspect we think that's important is what are the different tools and vendors available out there to help with this order? And are there any guidelines or standards around this? The third aspect, which is of course the most important and the core aspect around this, is performing that analysis itself, like the transmission hosting capacity analysis, to determine how much maximum injection you can do at particular one or multiple set of nodes combined under different reliability conditions or different operating conditions and so on. And finally, it's also important that as we perform these studies, as we develop these tools, as we make use of these resources, we share those experience and lessons learned with each other. So that's very important. Next slide, please. All right. And again, I think John covered well on what that particular reform within that FERC Order 2023 around the hosting capacity of developing that map, generating some relevant metrics, and some other specific informations around this. So we sent out this survey, as I mentioned. If you would like to participate, let me know. I can definitely send that survey to you. We can also share the complete results with you. Let us know. It takes few minutes to fill few multiple choice objective questions. Next slide, please. So I'll be sharing a couple of that results from that survey. So one of the questions, for example, we asked them that in what stage are you for this FERC order requirement? So whether you have already finalized the vendor or tool, are you still listing out the possibilities, or you haven't started yet? I do want to kind of note here that we started this survey a few months back, so some of this situation might have changed, but it kind of gives a good idea where the industry was at and moving forward. So there's approx 30% who were still kind of in making plans or haven't started the process, but most of them have either in a middle stage or some of them even executed and finalized which tool they want to use and how they want to follow with the procedure. Next slide, please. The next important question for us from our perspective was that, okay, how can EPRI help you guys to meet this order or in general in any other aspect? So we provided this different options, and as you can see, it was kind of unanimous that we could help in multifold ways. And so we are ensuring that our research and development, what we are doing here at EPRI, kind of aligns with these needs and other FERC orders or needs that industry require to assist them in moving forward. So next slide, please. Next slide. So getting into the tool itself. Now, although the focus of today's topic is particular feature of this tool, which is to calculate the hosting capacity, transmission hosting capacity, but the tool does have some other features as well. For example, if you want to determine, let's say, where you want to install or where your upcoming data center or load growth will be, this tool can help you with identifying and performing those things as well. But we'll not go in details on that aspect and focus on hosting capacity for today. And the tool we developed is compatible with many commercial solvers out there, including PSSE, PSLF, Power Factory, and so on. Next slide, please. Next slide, please. So the main framework in this tool, it can be divided into 3 pieces. The first one we call the scenario development module. What this does is it takes all the different relevant information from the user. It could be your different generation dispatch schemes or your retirement schemes. It could be different operating conditions, like you are analyzing your winter, summer, or different contingencies into considerations, or different load levels coming out from your different research or other analysis. So it takes all this information and creates all those combinatorial possible scenarios before it sends that setup to analysis module. Because when we determine the hosting capacity, we want to make sure that we analyze it from all different perspectives and not just focus on one. So we want to make sure the value we get respects all the different requirements by user or the FERC or other needs there may be for the operators or planners. Then the analysis module takes those scenarios, performs those different analysis, power flow or short circuit, and identifies, so what's the maximum injection or hosting it can do until it hit one of these different constraints, be it thermal or congestion or voltage limits or even short circuit ratio in this case. And once it completes the analysis, it finally sends out to the output module to disseminate that information in the output files, where it will show you that results of how much hosting capacity you can do at each of those nodes, what were the actual limiting constraints, like was it thermal, which line it was the factor that's limiting this hosting capacity. So all that information is spit out from this module, which can be then read by user or further analyzed or do most things with it. Next slide, please. So to sum up, like what kind of value can be provided by this tool? So that's the process we just learned. So it can do a bunch of different things, as I kind of covered in the previous slide. So if you have, let's say, multiple interconnection requests, it can compare that. If you have different generator retirement schemes, it can allow that as a user input. You can, from the dynamic stability point of view, let's say if you want to restrict the short circuit strength at a particular node for stability reasons, you can do that. You can provide a bunch of different contingencies to consider, different operating or loading scenarios, like as I said, winter, spring, light load, peak load, summer. So you can provide all those different scenarios for it to consider, and the tool will provide the least, or the worst case is what you can host, right? So that you do not violate any limits in any of that situation. And it can further provide a customized user selection to select a few set of areas. If you want to focus and not the entire system, then you can do that too. So you just monitor certain zones or areas as per your requirement. So it has that flexibility. Next slide, please. And to add on to that, so it basically provides that hosting capacity value at each node, and it does not assume copper plate model, basically to say that it runs that full AC model analysis when it is performing that. So it kind of get more near to accurate results. And as I said, it considers different those generator retirement profiles as you have this new generation or injections coming in. And we also recently developed this kind of miniature version of the hosting capacity heat map. And it's again customizable. Here particularly, we have grouped this dots or bubbles in the hosting meter range. So 0 to 100 megawatt, 100 to 200, 300 and above. But you can also specify a different kind of categorization based on zone or voltage level or area. It's easily customizable, but it's not as fully comprehensive in terms of like that interactive website, which some other tools were showing, but it was just to give a good visualization or good visual look or where those hosting capacity looks like throughout your system or grid. So next slide, please. Now, I do want to stress on one important point, which is sometimes I feel kind of left out in other conversations. When we do this hosting capacity analysis and you perform that considering one node at a time, that could give you, sure, like how much you can inject at that node. But let's say if as a transmission planner or you want to you have multiple point of interconnections now, and you are trying to inject or find how much total you can inject collectively, that could be totally different than just summing up individual analysis. For example, here we have this 39 New England bus system, just again as a sample example situation. So if you analyze bus 3 or bus 16 independently, so just one bus at a time, you can see it's roughly 1800 and 3000 megawatt, totaling to 4761. But if I collectively analyze where I'm trying to inject at both buses at the same time, slowly incrementing, you will see that the total injection is smaller. The total hosting meter or capacity is much smaller. So it's important that when we consider those multiple point of interconnections or cluster studies, that collective hosting capacity could be much different than when you just sum up individual POI. So that's important to remember. Next slide, please. We have done several studies using this tool with utilities and system operators. And in general, the objective was to determine or identify like a suite of different potential IBR or DER connections. Also to evaluate multiple scenarios at the same time, and also identifying what are those limiting transmission corridors or which limits are what constraining that hosting capacity. So those are in general, and I'll talk in more detail in one particular such study. Next slide, please. So this is a study which we did with NIPA, and the objective here was to analyze the hosting capacity of the entire zone together, but also independent or individual substation. So there were 14 substations in the area they were interested in. Next slide, please. And the findings, one of them was, as I just explained in the previous slide, in using the small example, the regional hosting capacity when you consider entire zone as together was much less than combined individual substation hosting capacity. So again, to highlight or stress is that when you have multiple POIs and generation coming in, we want to make sure that we analyze them collectively and not just one at a time. Next slide, please. The second finding, and also kind of obvious into build, is that the contingency, the set of contingency you consider, and you could have this set based on your historical understanding or from some other aspect that these are some of the critical contingencies, or maybe just all the N-1 reliability contingencies. That could play a critical role in determining your hosting capacity. So as you can see, if you consider just like the single contingency categories, then substation 14 was the least hosting or limiting. But if you consider multiple contingency category, substation 10 was least hosting capacity. So defining a correct set of contingencies also play a key role in identifying or providing you the more accurate or realistic hosting capacity value for your system. Next slide, please. And finally, the overall, it was determined substation 1 independently was having the most hosting capacity feature or availability. And as part of this study, we also identified what were the limiting constraints or paths for each of this substation analysis. But not just that, we also identified what are those common limiting constraints which were reflecting across multiple of this analysis. So these were some of the key findings that we got from this study. Now, one important question, right? Next step is that, let's say as a planner or as a developer, or you don't want to, let's say, put all eggs in one basket. Like you don't want to put entire generation in substation 1. You want to distribute or pick multiple interconnection points to install or for different specific reason. The question is, if you have that kind of problem, like we want to identify multiple location, how would you choose that? Like you have 14 substation, how would you determine which few locations are the most optimal choice? So that's what I'll talk about. Next slide, please. So we recently developed this optimization-based approach. We are still testing its features and things, but just to give you an idea and insight. So let's say you have 6 locations at your disposal, and you want to pick 3 of them. So as again, the problem statement is which 3 locations you would pick. And the result could be kind of drastically different depending on which 3 locations you choose. So for example, if you have bus 1, 2, and 14, the total hosting capacity here is 3318. But if you have bus 3, 9, 16, then you have 5,799 megawatt. So how would you choose what is the optimal choice of those X or subset of location among many choices? If you try to do it manually, it could take several combinations to analyze. And that's where we were like, okay, we need this optimization-based approach to identify that optimal subset of POIs. So that's why we were developing this approach to address that problem. Next slide, please. The next question from there was, okay, so far we were analyzing how much your grid, like with the existing infrastructure, what's the maximum hosting capacity, right? We had a great session in the morning around grid enhancing technologies. I won't go into what those GETs or grid enhancing technologies are. You can refer that earlier session in the morning or just type in the Google. There's a lot of information out there. But the idea for us was, okay, is it, and it's also coming from that another aspect of FERC Order 2023, where now when you perform or the generation interconnection study, the planner also needs to evaluate those 8 different alternative transmission technologies as part of solution to assist in that interconnection. And some of those technologies are part of GETs. So our idea was, okay, we take the system. So for example, here, the WEC case, we performed the hosting capacity analysis in a usual way. We identified the maximum was 3,000 megawatt. Now, the question was, can we make use of one of these or some of these GETs technologies to further boost or improve the increased utilization of the network? And we use another tool for doing that. It's called cPlanet tool to identify the best location, the size, and also what should be the control setting. We installed a power flow control device where it was to assist or help the area where it was hitting that limit. So to kind of make sure that that line doesn't get overloaded. And we installed that, re-performed the hosting capacity analysis, and now it boosted to 4,500 megawatt. Now, here I'm presenting one result, but we did this exercise kind of in cycles to keep boosting that to a much higher value. Now, I did present about this tool in the last year's FERC software conference. I have given the link if you want to check out. But the idea or takeaway from this is that it might be helpful not just performing hosting capacity analysis, but also to identify some intermediate or immediate tools that we can leverage to further boost that capacity. So to keep further exploring synergy with some of the other grid enhancing technologies as well. And this also kind of showcases our opportunity to how we can combine some of these different tools we all have been developing effectively with each other for, again, making or taking that one step forward, right, towards that cleaner green energy goals. So next slide, please. So to conclude, overall, we will basically to continue performing more case studies and trying to align with meeting those FERC order requirements. We will continue expanding the tool with those new methods, as I explained, like the optimization-based approach and exploring that synergy with some of the other grid enhancing technologies as well. And then more importantly, we want to start developing some guidelines and assessing like what would be the metrics you can compare the performance of different tools or methods, which one to pick for which application. So those are some of the guidelines which we feel could be helpful to industry and everyone else. And then most importantly, as I mentioned at the beginning of the session, to keep sharing those experiences and lessons we'll learn as we move forward with these kind of studies and development. So with that, I think I'm open for questions. Oh, next slide, please. Last but not least, all this is not possible with the great team we have here at EPRI. So I really want to thank and acknowledge each of my colleagues and teammates who are driving force kind of behind this work. So with that, now I'm open for questions. Thank you.
Thank you, Swaroop. Do we have any questions from our in-person audience? Do we have any virtual questions? Going once, going twice? All right. Well, let's give Swaroop one more round of applause.
Thank you.
And we'll welcome our next presenter. That will be another pair, is actually a pair of presenters, virtual presenters, Robert I'm going to get this wrong, Nyiredy, and Arne Bruflat Svensson. They are both from Infinigrid, and they will be presenting on a novel, unique, and proven approach to performing near real-time probabilistic power system risk analysis as an immediately available solution for unlocking existing grid capacity by facilitating the safe encroachment into N-1 power system engineering. Gentlemen, please.
Thank you so much, Alex. Can we go to the first slide, please? So while we're waiting for that, it was a long title, but the title in a short version is Seeing Through the Grid Complexity and Enabling the Green Transition in a Safe Way. Please, could we get the slides up?
Robert, we're looking at, okay,
Thank
great.
you. There we go. Thank you. So next slide, please. So we're going to talk about the current situation, which we see globally, not just in the US, but also in Europe and other places. The main goal of utilities and the main task, describe the problem, the challenge, and how the Infinigrid solution, ProMaps real-time, actually solves all these challenges. So with that, I will let the word go to Arne, our founder and CTO of Infinigrid.
Thank you, Robert. And can we have next slide, please? Yes, thank you. So our power grid, often referred to as the world's largest machine, that needs to be in constant balance and play in perfect harmony to keep the lights on. It's immensely complex, and it's the greatest achievement made by mankind. And this is the foundation of our society. Next slide, please. So this foundation is now being threatened by a worldwide gridlock that may slow down, or in worst case, stop the electrification of society and the green transition. So Rystad Energy states that there is a need for $3.1 trillion in investment in the power system by 2030. And this is not going to happen, and we are out of time. So there will be no transition without enough transmission. And this may lead that we start, the music may stop. Next slide, please. So the cause, the effect, and the needs, the change, the green transition and electrification of society. So the challenge, we changed the production fast, and we increased load by a lot, and there is a slow change in transmission capacity. So the consequence of this is reduced energy security, higher, more volatile energy prices, business that's going bankrupt, political instability, and basically a threat to our society. So there is a need to increase the capacity and the flexibility in the energy system to ensure balance and the security of supply. And the solution, that is to coordinate a multilateral cooperation on the development and operation of a power system with new system inside. So we need a better energy system inside for better utilization and for better coordination of the future power system needs across companies and across nations. Next slide, please. So how? We need to establish a common risk decision currency. And by analyzing and quantifying the current and future security of supply, so we can plan for a correct and sustainable risk level in a power system. So the graph shown in the middle of the screen here is a graph of the security of supply of a large power system. So basically, the higher the graph, the higher the risk for not supplied energy in the system. So by knowing the past, calculating the risk level and the security of supply in a real time, we have 2 points to give better prediction for the coming risk level in our power system. Next slide, please. So what we need to do is to utilize the power grid closer to its limits and freeing the needed capacity in a safe way. And the opportunity for grid operation, we need to use some of the spare capacity and by tapping into the existing security constraint in a safe way and give grid operators more road to handle the increase in traffic. And this can only be achieved by analyzing the security of supply in real time and understanding the risk and mitigate it when needed. Next slide, please. So the power system, there is a main task and there is a main goal. And this is the same for all utilities across the world. So the task is to ensure a constant balance between production and load at all times. This flow balance needs to operate within a narrow electrophysical band of frequency and voltage. The goal, however, is supplying demanded energy with as high security of supply as possible at as low cost as possible in all time span. This is the same for all utilities. And what we are focusing on is quantifying that goal. Next slide, please. So we all know the problem, but just to give us a summary of that, we increase the load fast, we change our production, and there is not enough production at all times, and there is a slow development of the power system. So we increase the load and we change the production in terms of years, and the time it takes to upgrade our power system is a decade. So basically we have a system problem on our hands. So we change too many factors at the same time in our power system now, so something has to give. Next slide, please. So the challenge that we are facing with the N-1 criteria that was developed many years ago, 1950s, we have had a pretty stable state until now. And the N-1 criteria, that is the foundation of our power system, has been functioning very well and has ensured a high security of supply and low risk in the power system. But now we are entering a new period where the new normal will be an abnormal state for the coming decades. So, and before we reach some kind of a stable state. So in this phase, we need to increase visibility and transparency to obtain more flexibility by using new analytics to understand the current and future risk of our power system, and thereby adjusting system operation and investment based on the best mitigating risk measures. Next slide, please. So imagine if we can see through the increasing complexity in our power system. Imagine if we can gain new insight, giving better flexibility and higher utilization. And imagine if the key for opening the gridlock was right in front of us. Imagine what we can do. Next slide, please. So the solution here is to quantify the risk level probabilistically in their real time. And then there is possible to see the effect of all the planned grid action that is being planned, from the storing energy system, spinning reserve, load flex, load shedding, new grid investment, production impact, and of course, optimized system operation. And by doing this and quantifying the security of supply probabilistically and getting the risk of the whole system in their real time, we get a better insight and a better precision in our decision. And also, it's possible for all stakeholders to evaluate the risk affecting all at the same time. Next slide, please. So the software that we have developed is based on new mathematics, where we have solved the dimension problem with the Markov model. And we have developed a software called PowerGEM Real-Time. And we'll go into how this may help the situation in our power system now. Next slide, please. So, as I said, so it's a probabilistic risk analysis tool for utilities. It's near real-time analysis for system operation and scenario analysis for longer timeframes, where we predict the expected not delivered energy and the connected cost, and therefore connect to the main goal for utilities. And when we have the baseline constantly updated in near real time, we get good use cases, not only for system operation and planning operation, but also for preparedness planning, maintenance planning, reinvestment, and long-term investment. And all of this information can be aggregated to the top management. So everybody in the utility have the same picture of how we are in terms of reaching our goal for the utility, which is have as high security of supply as possible to as low cost as possible at all times. So as I said, the way we have solved this is by using a Markov model combined with Kronecker product operators that we're using, so we can model the power system and all its components in high degree of detail. So our system is data hungry, and in our times with the digitalization that is going on all over the place, we have a place to put all the data and get new system insight. Next slide, please. So basically what we are doing, we have do a power flow analysis combined with a reliability calculation. When we combine this, we can calculate the expected not supplied energy for all load points and the system as a whole. And when we quantify the expected not supplied energy, we can connect the value of loss of load to this value. So system operation gets a new tool in a toolbox to do proactive risk mitigating action based on the risk level in the system. Next slide, please. So as I said, we are using small Markov unit models representing each primary and secondary component in the system. So basically, failure rates and repair time, reconnection times were put into the specific unit models for each component type. And in addition, when we can model each component in high degree of detail, all available data and information from the asset management system can also be included, adjusting our failure rates, so we can get a good picture of the state of the power system based on the state of each or all of our components in the system. Next slide, please. So some of the mathematical foundation. So the macro model is given on a differential equation. So what we basically do, we can combine two different Markov models with the Kronecker product and get the total state space, probability state space for the combined model also on our Markov model form. And we get the full transition rate matrix by combining the A matrix for both models with the identity matrix for both of these models. Next slide, please. So the result we get from this calculation, on level 1, the reliability result, of course, the probability of failure per component, probability of failure per network segment, and probability of system failure. That's basically the reliability analysis of the power system. When we combine with a load flow calculation, we can calculate the expected energy not delivered and calculate all the risk indicators for a system. And we get a contingency, risk-adjusted contingency list that takes into account the probability for getting a failure on that branch combined with the consequence. And combining all contingency within our reliability threshold, we get the total system risk that is shown on one calculation as 1 point on that graph. And this is going in there real time. We get a graph that basically is the inherent property of that power system. Next slide, please. This is an overview of our dashboard on the left, on our desktop version on the right. So as I said, the contingency list, the sum of all contingency will be the expected not supplied energy that will correspond to 1 point on that graph. The risk speedometer shown on the left there is basically setting the level that is the desired risk level to operate within for the utilities. In a green state, this is a system minute indicator that corresponds to, if this situation would be the same for 1 year, it corresponds to 43 minutes for not supplied energy in this system for the whole load. So this is on Iceland. So below 50 system minutes is okay. Above 50, you are in the yellow range. Then the system operator should consider doing an action, test what to do in the desktop version, and do what if analysis, and put the best action into operation before the risk increase more. Next slide, please. So just to go into some of the use cases. Use case number 1, system operation and planning operation. This is basically for system operation, where one look at the screen, the system operator is to understand what's the current risk and what to do. And for planning operation, when the system operator comes to the shift, you get a risk forecast for the next 12 hours, giving the risk level, where the risk calculation is combined with the weather data as well, and what action he or she should take if this occurs. Use case number 2, and here we create more flexibility in the power system by coordinating TSO and DSO system operation for two different utilities. And if both are doing the risk calculation we describe here, and the risk result, calculation result from one area follows the flow into the next area, the impact from the neighboring utility will then be shown in the calculation at both of the companies. So when the root cause is affecting both, the risk level will increase in both utilities. Then they can pick up the phone and coordinate what's the best action to do, not only for their utilities, but for the overall system. Use case number 3, this is the same principle where we have TSO, a large consumer of power. If the large consumer of power have a similar risk analysis software as we are describing here, and are doing the analysis of the power system risk in the infeeding and surrounding power system, when the risk is increasing over a certain level, they can then choose to reduce the production, in this case, aluminium. And by doing that, reducing the stress in the system and reducing the risk. So this can be then coordinated by system operation for large consumer of power with the TSO. And the last use case for investment analysis, is very important that you have an accurate picture of the future state and the future risk situation in your power system when you're evaluating which power system investment you're going to do, A, B, or C, and can you postpone it? Next slide, please. Yes, that was the last one, summary. So Promos real-time software as a service that give a new quantifiable insight in how capable a utility ought to perform their main goal now and in the future when facing today's unprecedented challenges. So this insight will help our customer increase profitability by reducing cost, reduce the silos in the organization by quantifying one common reality, and increase flexibility and thus freeing needed capacity in the power system and doing the correct action at the right time. So the future will be probabilistic in all power system decision, and Grid are the only one capable of providing this insight with our software solution as we know of. Yes, thank you.
Thank you, Anna.
Thank you, Robert and Arnie. Any questions from the in-person audience?
Nicolas Aumont from Artelis. I saw that you presented slide about Landsnet in Iceland. It's a relatively small system where it's quite easy to do a post-contingency analysis to do how much curtailing energy you have. The cascades are rather small, but how does it extrapolate to a big system where the cascading and the blackouts can cover a very large region and are not easy to simulate?
Yes, so you're correct. So the Icelandic power system is a perfect place to test it because you have the control of all the whole power system. So we have done this for the Norwegian power system, including a large part of Sweden and Finland as well. So how can I explain this? It's you need a very flexible mathematics at the bottom here to be able to do this on large power system. So, and you need to do stack your calculation in a way that you can scale this in a good way. And that we have done and been developing for many years. So now we are capable for doing large power system in their real time. So yeah, so we are ready to test this on a huge power system. That is should be possible for us to do.
I think we have a virtual question, or do you want to go here first? Okay. Please introduce.
Yeah, my name is Felix from Great Insights. My question is, I guess you have to rely on heavily on historical outage data of the transmission line, transformer, and breakers. The issue I had before is if you look at the outage history, it is, of course, there's certain area will get a lot of lightning, will have a lot of outage, but they will have a very, very long tail. There will be maybe 50 or 60% of the transmission line in my area will have, one or two outage in the past year or two. And then some even happen in the next year, those long tail event will change drastically. And also in the context of, extreme event, extreme climate, especially in North American, how could you deal with this kind of, the first is long tail event, the outage rate, and the second is extreme weather. Thanks.
Yeah. So what we do is we are basing all our input on the failure rate for each component, and for the power lines we include weather forecast also. So what we do, and we have done in Norway, we did a R&D project with the weather company Storm Geo, where we looked at all the failures, different failure type on the transmission line, and including the weather. And the weather itself, we focused on the wind in this case, was 23% of the failure on that failure rate for that specific voltage level was due to wind. So what we did a correlation with the outage connected to wind, and we adjusted the failure rate, the 23% of the failure rate for that power line, according to the increase of wind speed. So what we are doing, basically, we are taking in the weather forecast and changing if there is high wind speed or it's lightning. So the same principle will goes for lightning as well. If lightning is coming into an area, we want that part of the lightning, part of the failure rate to increase accordingly as the lightning is nearing the power system or the power lines in that area. So in that sense, you get this insight into your calculation. And the big difference there is, since we're doing this in real time, we're constantly updating this. When the weather is increasing in wind speed or what have you, you will see that the risk is increasing in the power system as it should. But when the weather is good, the risk is lower than the average. So we have this change based on the external factors putting into the system. And also a good test of this is when you're doing this calculation in real time, updated every 5 minutes, for example, you get a sense of how the risk level is changing, and the system operators are the best critics to see if this system is quantifying the risk level. They have a gut feeling it's increasing now. And also you can test and see how the system, how the actual outage you get, and how the calculation you did cover that with the actual increase in risk result that the system is producing. And we had an animation from the Icelandic power system. I was not able to show it now, but that was, as you're pointing out, bad weather was coming in over Iceland. And you see the normal state as the weather front was approaching. And then you see as the wind hits Iceland, the risks start to multiply a lot. And then you get the actual outage as well. So then you can see, did the calculation foresee this outage, this type of outage on the contingency list, moving up on the contingency list as the wind was increasing? Yes, I'm not sure I'll answer your question fully, but it was an attempt.
Yeah, I'm just thinking my experience. We in my area, most of the force contingency lightning related, and it's sometimes when you're giving a prediction for the risk, you want to separate that from just monitoring the weather, because they already done that in the operating room. But I think overall, I really want to say, as my experience before, I guess we all know, right? N-1, the 1 is not equal. My experience, there's a certain 500 transmission line in my area always get outage. There's vast majority of the other transmission line never get outage or very few. So when you do your transmission planning, actually, we were using in my last employer already is putting the probability into the transmission process. And I think that probably will be a great use case for your methodology. And thank you for that.
Thank you. Any other questions from the in-person audience? Do we have any from our virtual audience? Going once, going twice? All right, let's give them another hand of applause.
Thank you, Alex. Have a great day. Bye.
Thank you. Bye.
Thanks again. Our final presenter for this session will be Alenson Santos Javier from Argonne National Lab. Alenson will be presenting on analysis of market-to-market coordination. Alenson, please.
Thank you. Thank you everyone for coming to the session. My name is Alenson. I'm a computational scientist at Argonne National Laboratory. Yeah, and today I would like to show some early results that we have on market-to-market coordination. So there's this joint work with Wei-Han Ren and Yongpei Guan from University of Florida, Fengyou Wan from New Mexico State University, and from Fanqiu, also from Argonne. And I also like to say that most of this work here was done by Wei-Han Ren, so I'd like to thank him for that. Next slide. Oh, good. Yeah, so I think most of you might already be familiar with market-to-market coordination, but I would still like to give a brief introduction. So as you probably know, today the RTOs essentially run very separate system scheduling and operations. So essentially they're quite independent. For example, they run their own unit commitment problems, economic dispatch problems, and they figure out how to best use the resources within their regions. The one issue that we have with that is that sometimes decisions that they make have impact on the neighboring regions. So here I have a quick example. We have two RTOs, A and B, and you can see here that although RTO A is dispatching a generator to serve a certain load within its own region, there's a loop flow that actually goes outside of its own region, goes into RTO B, and then it flows back into RTO A and finally serves the load. And in the worst case scenario, you could see that a dispatch within RTO A could actually generate a congestion within RTO B. So for this reason, it is very important that the two RTOs work together in managing this kind of congestion, right? And you could think of many different ways to do this kind of coordination, but some high-level goals that we should have are our first one. It would be better if we could manage the congestion using resources from both RTOs. In this way, we can assure that we are getting the most cost-efficient solution to manage the congestion. And the second thing is, it's also important to take into account the value and cost of redispatch or curtailment. So one thing you don't want to do, for example, is to have a list and say, if there's a congestion in this transmission line, you automatically change a certain dispatch because this wouldn't consider the value and cost of redispatch. So the final goal, if you do this correctly, would be to align the border prices and to just reduce the overall cost of congestion across both systems. So this has already been done by multiple RTOs. So since 2005, MISO and PJM and MISO and SPP have these joint operation agreements where they describe how exactly they're going to coordinate. And also since 2013, there's also an agreement between New York ISO and PJM. Next slide. So there's also quite some research on this. I just listed a few papers here. And essentially what these papers are trying to do is to analyze how exactly do these joint operation agreements work? What are some potential shortcomings and how can we improve them? So, for example, some of the challenges that they pointed out was these systems worked pretty well, but now that we have more renewables and more fast-moving units, we are seeing that these algorithms are starting to have some challenges. Specifically, one problem that multiple papers listed was this issue of price and the power flow oscillation, which I'll go into in a future slide. But there are also other shortcomings and some other things that they propose, such as improving the way that the RTOs calculate this thing called the request relief request amounts, and also even identifying which constraints in the network are the most suitable for this kind of market-to-market coordination. Okay, next slide. So in this talk, we have 4 main contributions. The first one is we actually start by formalizing the problem and proposing a centralized formulation. Our goal here is first to just make sure that we're all on the same page working on the same problem, but also with the centralized formulation, it gives us a lower bound so that we know how good are these methods compared to just the theoretical best. The second contribution that we have is that we actually implemented the market-to-market process, and then we did some evaluation on some synthetic systems to see how well do they perform. The third contribution that we have is that we actually propose a new method based on decentralized optimization, specifically using AGMM, and I'm also going to show one example on its convergence. And finally, we are planning to release all this as open source software because our goal is to. It was a bit hard for us to get started with this. Implementing these methods was actually quite hard. So we hope that with these open source packages, we can accelerate the research into market-to-market coordination. Okay. Next slide, please. Yeah, so I would like to start from the centralized formulation so that we actually formalize exactly what problem are we trying to solve. So this market-to-market coordination problem is essentially a multi-area security-constrained economic dispatch. So the way it differs from the regular security-constrained economic dispatch is that we have 2 regions. Here I'm going to focus on 2 regions, right? And then the generators and loads are essentially split into those 2 regions. One constraint is that the load must be served by generators within its own region. So in this problem, we don't specifically try to optimize how much should one region export to the other. We just assume that they are importing or exporting a fixed amount. And we also assume that although the generators and the loads are split, they are sharing the same transmission system. So here on the right, I have the formulation. You can see here the objective function is to minimize the production costs. And by the way, this is a simplification. The actual formulation can be more complex than that. But we minimize the production costs. Then we have the generator constraints, which in this case is just a minimum and a maximum power balance. Sorry, we have the power balance constraints, and we can see that we have 2 sets of power balance constraints. One is for the load, for area number 1, and one is for area number 2. So essentially, you only sum the generators within that region. We also have this delta to account for any imports and exports from one region to the other. You can see that they cancel out, and these are not variables. The delta is just a constant. And then I guess the most different part is in the transmission limits. You can see here the last equation says that the sum of 2 different flows have to be within the limits. And this is the flow coming from RTO1 and the flow coming from RTO2. And then we compute these 2 independently. So FL1 is just the shift factors times only the generators from region 1. And then FL2 is the shift factors times the generators from load 2. And if you solve this problem, you get 2 main sets of decisions that you optimize for. The first one, and I guess one of the most important, is you can actually get the dispatch. So you know what is the power level of each generator in your network of both RTOs. But also another very important output of this multi-area security constrained economic dispatch is actually, because we computed the flows separately, F1 and F2, we actually now know how to split the transmission capacity between the 2 RTOs. Okay. And this is going to be one of the main outputs. Next slide, please. So here I have a very small example. This example is adapted from a 2017 paper. So here I'm just showing how would it work with a centralized formulation. So in this example, we have 2 RTOs, we have 4 generators, and we have 2 loads. So we minimize 0 times P1 plus 40 times P2, which are the production costs for generators 1 and 2, plus 10 times P3 plus 6 times P4, which are the production costs for generators 3 and 4. So the 2 power balance constraints that we have are the 2 generators, G1 and G2, must satisfy the load L1, which is 300 megawatts. And then we have the 2 generators, G3 and G4. They have to satisfy the load 2, which is 350 megawatts. In this example, we are only concerned about 1 transmission line, which has a 600 megawatt limit. And this is the one where we're doing the coordination on. So we first compute the flows from each RTO. So from RTO A, the flow going through there is, you can see it's essentially the injection from generator 1, so F1 equals P1. And then the flow from RTO B is just the injection from the generator 3, so F2 equals P3. And finally, we have the joint transmission constraint, which means F1 plus F2 less than or equal to 600, okay? And then if you optimize this problem, you're going to find the optimal overall solution, which says that we have to dispatch the generators at a level at 280, 20, 320, and 30. And also you will get the flows that I mentioned before. So for that transmission line, you have two different flows. So from RTO-A, you're using 280 megawatts. And for RTO-B, you're using 320 megawatts. So this not only tells you how to dispatch the generators, but here it also tells you that the best way to split the 600 megawatt capacity between these two RTOs is to assign 280 to RTO-A and the 320 to RTO-B. Okay. Another thing that's not on the slide, but I would like to mention too, is that we can also use this centralized model to compute the marginal costs. And essentially, if you can see here, for RTO-A, if instead of a 280 megawatt limit, if they had a 281, this would be beneficial for them because then they could dispatch generator G1 1 more megawatt. Right now, they're restricted by that. So for RTO-A, the marginal cost is actually $40. However, for RTO-B, even if you increase the limit from 320 to 321, this doesn't make any difference because the generator G3 is already at its limit. So the production limit there is from 0 to 320, which is already the limit. So for RTO-B, the marginal cost is actually 0. Okay, so even though this is an optimal solution, you can see that the marginal cost on both sides can actually be different, and this will be important in the later slides. Next slide, please. Okay, so this was the centralized method. This gives us a theoretical lower bound, but unfortunately it cannot be used in practice because it would require you to build one large optimization problem with data from both RTOs. So what the RTOs have been using in practice is something that looks more like this iterative method that I'm going to describe in this slide. And here in this talk, I'm just going to mention a very, very simplified version of it. The full version is this diagram that you see here that we actually implemented, but I'm not going to all these decisions. So essentially, the first step is to actually identify which constraints in your network would benefit from market-to-market coordination, and these are called the flow gates. These are just the most significant constraint points in your system, and also that have impact from both RTOs. And then for each one of these flow gates, you assign a monitoring and a non-monitoring RTO. And the basic idea of how this works is the non-monitoring RTO, it starts without any constraint on that flow gate, so they use as much capacity as they want. And the MRTO will actually have that, in their economic dispatch, they would have that physical flow limit. And then what the MRTO does is if it detects that there's a congestion there, it will then calculate some information, so the shadow price and also this so-called relief request. And they'll ask the other RTO to essentially reduce its usage. So the NMRTO will then resolve the economic dispatch with this decreased limit, and the MRTO will resolve it with an increased limit. The idea here is that at some point they will find a balance where they are sharing the transmission capacity evenly, let's say. And essentially you repeat this whole process until the shadow prices converge from both sides. So I'm going to show a small example to make this more concrete, but this is just the simplified version of the method. Next slide, please. Yeah, so going back to the example that I showed before, this is how the iterative method would work. And by the way, this example came from the 2017 paper that you see here from Chen, Jin, and Mellinger. So to start with, RTO-A doesn't have any constraint. So they essentially use as much as they would like, which is 300 megawatts to serve their entire load. And then RTO-B, which here is the monitoring RTO, we'll see that there's only 300 megawatt left of capacity. So they will dispatch their own generators at 300 megawatts and 50 megawatts. And then that constraint becomes binding at 600 megawatt limit. And then you compute the shadow prices for both sides. From RTO-A, they would not benefit from any additional capacity, so it's a $0 per megawatt shadow price. And for RTO-B, it's $50 per megawatt. And then what RTO-B will do is to compute a certain relief request, which is 15 megawatts. And then it'll ask RTO-A to essentially rerun its economic dispatch, but now using a lower limit. So instead of unlimited, can you now set it to 285? That will cause a redispatch in RTO-A. And now RTO-B has some extra capacity that it can use. So now it goes up to 315 megawatts. And you can see here that after this redispatch, the shadow prices become a bit more similar. So for RTO-A, the shadow price becomes $40 per megawatt. And for RTOB, it becomes $50 per megawatt. So they are kind of approaching each other. And the idea here is that this procedure would continue until the shadow prices converge exactly, and then it would stop. Okay. Next slide, please. Yeah. So the most natural question that you would have after you see the description of this method is essentially, does this method converge? How often does it converge? And if it does converge, what is the solution quality like if you compare to the centralized method? So these were the research questions that we had. To answer these questions, we implemented both methods. We used Julia and Jump. We used an open source optimization solver called Heis. And this whole work is built on the package called unitcommitment.gl. So if you're not familiar with unitcommitment.gl, we presented at this conference in the past years. It's an open source software for unit commitment problem. It provides a data format for unit commitment. It provides a lot of instances and also provides implementation of state-of-the-art methods. So here it was very useful for us because we didn't need to re-implement everything. Essentially, we just asked for the base model from unit commitment.gl, and then we just modified the constraints to do what we needed. And we also used the set of instances that they had, and we modified those. So going into how did we modify these instances? So these are essentially from MatPower. We chose instances with 1,900 all the way up to 6,000 buses. And because these instances were only a single zone, we had to decompose them into 2 zones. And we also chose 1 flow gate for each one based on the shift factors and also on the flows. If you want to know more details, I can talk about it offline. How did we construct these test cases? Okay. Next slide, please. And here are some of the early experimental results that we got on the evaluation of this iterative method. So in this table, I'm showing the network that we are considering. What flow gate did we do the market-to-market coordination on? I'm also showing the cost if you actually solve this as one big centralized problem. I have a column for the iterative cost. The gap one is the difference between the iterative and the central one as a percentage. And then finally, I have a column saying whether the iterative method converged or not. So the first takeaway here that we have is that the method actually works well for some instances. For the case 1951, 3120, and 3375, the method converged. And not only it converged, it actually converged to the optimal that you get from the central solution, which is pretty good. On the other hand, the second takeaway is that as the instances become more challenging, as we had more congestions, then the method was unfortunately not able to converge anymore. And some of the gaps that we got were also pretty large. So this tells us that while the method probably works well in a relatively congestion-free scenarios, as you start to stress it, you also start to see deterioration in the solution quality. So essentially, there's still a pretty large margin for improvement, both in terms of convergence, but also in terms of the gap. Next slide, please. And here, I would just like to talk briefly about 3 conversion issues that we observed during our experiments. In the literature, they talk a lot about one of these issues, but we haven't seen anybody talking about the 2 others. So the first one is this one on the left. We saw that sometimes, even though the algorithm, the iterative method, even though it actually lands at the optimal solution, it doesn't satisfy the termination criteria. So the algorithm keeps going, even though it already found the optimal solution. The second issue, which is the one that people mention a lot in the literature, is called the power swing issue. And this essentially happens when the monitoring RTO asks for too much relief request, and that line which was binding essentially becomes non-binding anymore. It asks the non-monitoring RTO to reduce its usage so much that the congestion is entirely gone. And then in the next iteration, the non-monitoring RTO will remove that constraint and the congestion will come right back. So the thing that you observe is that the flows keep going up and down and the method never converges. And then one final issue that we saw, and we also didn't see this discussed in the literature, was that sometimes the 2 RTOs are using the same transmission line, but they are using it essentially in opposite directions. So what happens there is if there is a congestion in that line, what you would like the other RTO to do is actually to increase its usage. So you can also increase yours, and then one offsets the other. But to the best of our knowledge, the current methods, they only focus on reducing the usage. So they don't handle this case very well. Okay, so these were the 3 issues that we found. Next slide, please. Okay. Yeah, so just to finalize, I would like to describe now another method that we can also use to solve the same market-to-market problem, but it's not the iterative method that's currently used. is based on AGMM, which is a method called Alternative Direction Method of Multipliers. So if you have ever studied decentralized optimization, you probably heard of this method before. It's one of the most widely used methods. The good thing about it is that it has very strong mathematical guarantees. Essentially, if your problem is a convex optimization problem, which is our case because we're solving the economic dispatch problem, then the convergence is guaranteed. And it will guarantee, and not only will converge, but it will actually converge to the optimal that you would get by solving the centralized problem. It's also relatively easy to implement, and it's highly flexible, so you can customize it in different ways. And this method has also been successfully applied in a number of fields. So we, in previous research, have applied this, for example, to solve the multi-area unit commitment problem, where it performed very well. And people have also used this for many other problems, even in power system optimization. So it was a very natural question to us, what happens if we apply AGMM to this market-to-market coordination? So just to give a very brief overview on how does AGMM work, here we're using the specific variation of AGMM called consensus optimization. We're essentially trying to minimize an objective function, which looks like this one, minimize f1 of x plus f2 of x plus fn of x. And here, notice that we have the same x that we are plugging into multiple functions. But the tricky part is that we don't want to build one huge optimization problem that contains all of these functions. We would ideally like to minimize each function independently, right? So the basic idea for the method is that we create n copies of x, so one for each function fi, and then we optimize each fi independently, and we're gonna get n different values of x. And now we compute the average of these x's, and we re-optimize the functions f, but now we have some penalties. So essentially, you can still find different values for each function, but if you want to deviate from that average, now you have to pay both a linear penalty term and a quadratic penalty term. And then the algorithm just repeats that. It optimizes each function independently using these penalty factors. It updates the average, updates the penalty terms, and it keeps doing this until essentially all the xi's equal exactly to the average. Okay. Next slide, please. So in this slide, I'm showing now what it would look like to have an AGMM formulation for the market-to-market problem. So here I'm color coding. The blue color belongs to one subproblem, and the red color belongs to the other subproblem. And as long as the constraint is entirely colored with one color, that's not a problem. We can just move it directly to one of the subproblems. The only constraints where we have issues are the ones that have some terms that are blue and some terms that are red. But essentially, it's very, very similar to the centralized method. Objective function is the same. The generator constraints are the same. The power balance are the same. The power flow equations are also the same. And the only difference here would be in the transmission limits. So if you recall from before, we only had one transmission constraint. Now here we have two, one for each subproblem. And before we had two flow variables. Now we have 4 flow variables for each transmission line. Essentially, we create one copy of each, and we give one copy for each one of the subproblems. And then we have these consensus equations at the end. As you can see, we have a blue term equals to a red term. So this one will not actually be inside any of the subproblems. This will actually be enforced using the AGMM method itself. Okay, but that's just a rough outline on what it would look like. Next slide, please. And finally here, we're still running the full set of experiments, but I would like to show you one case, which was a particularly difficult case for the iterative method, the case 2383, which is where we had the power swing issue that so many people discuss in the literature. So here I'm showing 2 charts. The one on the left shows the global residual, so essentially how far away from consensus the variables are. And the chart on the right is the global objective value, so the total cost for both problems together. And ideally, what we would like to see in the residuals is that they go to 0. And in the global objective value, what we would like to see is for them to converge to the optimal central value. And this is essentially what we see. After about 10 to 15 iterations, the chart on the left, the residuals all go to 0. And in the chart on the right, you can see here that the value jumps up and down. But after 10 to 15 iterations, we actually get convergence. And this converges exactly to the value of the central method. So in summary, using AGMM for this quite challenging case, we didn't have any convergence issue, and we completely avoided the power swing problem that people have described in the literature. Yeah. Next slide, please. So just to conclude this talk, we presented a centralized formulation. Also, we formalized the problem. We did some evaluation on the iterative method, and we proposed a new way to solve it using HMM. So the takeaways here is that the iterative method works for some less challenging instances, but it still has quite some margin for improvement. And we also concluded that AGMM is quite a promising approach because it doesn't solve from all these convergence issues that we had in the past. So right now, for future work, we're still doing more extensive evaluations using more conditions, more load conditions, more congestion and all that. We're also doing some performance enhancements in our AGMM implementation, and we do plan to release all this as an open source software package. Yeah, and just to finalize, I'd like to thank the Advanced Grid Modeling Program from US DOE, which has been supporting partially some of the people involved in this work. Thank you.
Thank you, Alan. Any questions from our in-person audience? Looks like we got a couple.
Alex Rutkevich, Newton Energy Group. Out of curiosity, have you thought if there is a market mechanism that would actually achieve that convergence without sort of iterating between the RTO engines?
Yeah, actually, when we started the project, we were looking into that. Can we just make small adjustments to the algorithm? I think that it might be possible, but we haven't looked too much into it. We're also hoping that by studying the AGMM and see what does it do, maybe we can kind of reverse engineer something and bring it back just to a market solution.
Hi, my name is Sayed from Alpha Traxia. Well, first of all, thank you for the great presentation. I love that work. My question is that, first question, are you modeling different monitor contingency pairs as well? Is it actually security constrained, or you just did OPF on the two sides, DC OPF?
So for this work here, we're just doing the transmission constraint yet. But for the full work, we will have the security constraint version.
Okay. And my second question is, so when you're applying ADMM, you said that you're using consensus method. So are you solving the two RTUs in parallel first and then do consensus?
Yeah, so the subproblems are solved completely independently in parallel.
Yeah.
So you solve each subproblem, and then they share a little information, which is just a flow on the flow gate, and then they resolve it.
Okay. Yeah. Have you tried schedule consensus where one solves, like basically because you only have two groups, so it becomes sequential?
We have not tried that. It could also, it'll probably also work.
We did apply it in a different problem, and that actually reduced 10x the number of iterations.
Oh, okay. Yeah. Yeah, actually, the ADMF has a lot of hyperparameters that you can tune. We didn't tune it very well, so we see that the objective is jumping quite a lot. I think if we actually fine tune it, we could get much faster convergence. Yeah. Thank you for the question.
Do we have any virtual questions?
One other question in the room.
Do we have any virtual? Yeah.
Okay. Yes, we do have questions online.
All right. We'll take our in-room question first.
Thanks. Mary Wiersbicki from FERC. Could you talk a little bit more about what made that problem challenging that you presented at the end of your presentation?
What makes the market-to-market coordination challenging?
Yeah, or specifically the one you simulated that you showed the results at the end. I just didn't understand what about that particular one was challenging.
So that example, the 2383 case, was particularly challenging because it had the power swing issue that people have described before in the literature. So what happens there is that at first the line is congested, and then the monitoring RTO asks for some relief. And then the non-monitoring RTO starts to back down on the usage of that transmission constraint. But then the MRTO keeps asking for more and more relief until it reaches the point where the line is not congested anymore. The non-monitoring RTO backed up so much that there's no congestion there anymore. And then what happens in that case is that constraint essentially drops from the market-to-market procedure. And then the next time step, the non-monitoring RTO can essentially use as much as it wants again. So it goes right back to being congested. And then the process just repeats over and over again.
Got it. Thank you for that explanation. With your simulation, can you also look at the time lag? I know we've heard from some RTOs that because of the way the settlements work on the two sides, it takes a while before the imports show up to help a problem. Do you see that at all, or are there ways you can simulate that with the tools you've built?
Yeah, that's a very good question. I think the question is whether we could simulate the conditions changing over time, right, as they run the algorithm. We didn't implement that yet. It would be possible. We actually wanted the most simple case for the methods where the conditions remain the same. Because also some papers describe that was the issue, right? The conditions keep changing, so the method cannot converge. And what we have seen is even if the conditions remain the same, the method still has some issues. So it might be something more fundamental about the method. Thank you very much.
Do we have a virtual question?
Hi, Alondro. I'm going to go ahead and unmute you so you can ask your question. Okay, go ahead.
Hello. I had a question about what might be some of the downsides to using the ADMM method. Particularly, does it take longer to use this than the current iterative method? Or what might some other challenges of implementation be?
Yeah, thank you very much for the question. I would say the biggest drawback of using ADMM is that it requires new software. It's very different from what the RTOs are currently used to. It requires specialized software for optimizing that. In terms of computational complexity, it's probably higher, but I would still say it's not a prohibitive thing because the original problems are linear programming problems and they become a quadratic optimization problem. So it's not that big of a deal. I think implementation-wise, like having the software to do it, I think that would be the major bottleneck.
We have another in-person question.
Pablo Ruiz, Brado and Nugget. I have a comment, more than a question. I would be interested in your reaction. The issue with coordination across LTOs or market-to-market constraints can be of two types. One is delays or differences in the shadow prices or the information reflected in each market. That could result in oscillations or maybe some differences. The other one is more structural. So the other one is when you have constraints where there's an asymmetry in the units in each RTO such that one RTO may have really good shift factors or upstream or let's say positive for a given constraint, but really bad or very low negative shift factors and the opposite occurs with the other RTO. In that case, absent formal ability of the RTOs to transact between each others or an ability for the units to move between the RTOs, then you just cannot reach an optimal period. If you're artificially, or not artificially, but if you're limiting the units that one RTO and the other RTO can control. So I was wondering if you have seen the second and any thoughts for how to mitigate it.
So it sounds to me like this would be more of an issue on deciding how much to import or export. I may be mistaken, but it sounds to me like more of that. And we have been focusing mostly on congestion management. Yeah, but I do think if you're trying to optimize the amount of import and export, that could be an issue too.
Yeah, and that asymmetry usually leads to a very significant shallow prices in the market-to-market constraints as compared to the non-market-to-market constraints. Since you're fighting, with very different types of shift factor differences.
Yeah, thank you for the question.
I think we have one more virtual question. Go ahead.
Hey, Alondro, I'll go ahead and unmute you again. All right, go ahead.
Thanks, Monica. I had a question about one of the non-convergence issues that you described, a third one where they're trying to flow on opposite directions on a line and they actually increase power. Does the ADMM method resolve this? Can it see that as a possible solution in that direction, whereas the current method doesn't?
Mm-hmm. Yeah, so as far as we know, the ADMM method solves all the three issues that I mentioned. The termination criteria is well defined. and is also able to handle that, the opposite flows. Yeah, thank you for the question.
Do we have any further questions in person?
The scheme seems to be quite complex to set up. Are there already simpler scheme in place, like capacity splitting based on forecasts or something similar?
I'm not the best person to talk about that, but from my understanding, the RTOs already have some pretty complex ways to split the capacity of the transmission lines.
Any further virtual questions? Going once, going twice? All right, let's give Alan-san another round of applause. All right, thank you, everyone. That concludes this session of the conference. We'll be resuming sessions at 3 p.m. in this room and the commission meeting room. We'll see you then.
So let's begin the session W3B, I believe it's called. And the first presenter, it's my honor to introduce former chief economist of FERC and the founder of this conference, Dick O'Neill, and his presentation is titled Completing ISO Markets, if my memory serves me correctly.
Thank you. Well, somebody put the presentation?
Yeah.
Okay. Huh?
It's for suspense.
Oh, there it is. Okay, my talk today is entitled Completing ISO Markets. What I'm going to try to say or convince you of is that there are certain things we should be doing to move the efficiency of the market forward. Next. Okay. You know, what we've seen over the past 2 or 3 decades is that the vertical integrated utilities have taken essentially a backseat to the ISOs, who have grown significantly and continued to grow, and now have somewhere between 60 and 70% of the market, and that's growing as we speak. You know, I'm going to talk a little bit about reliability, a little bit about pricing, a little bit about beneficiaries pay. My feeling is that beneficiaries pay is the heart of regulation. It's essentially a different side of the same coin of cost causation, and it mimics what you would see in a competitive market. One of the subsequent issues is the fact that we need much more and faster computational capability in order to deal with these things, especially sitting through some of the DER presentations. I realize that these things are essentially going to complicate the computational issues significantly. And the question is, how do we deal with some of this stuff? Next. All right. What we think is going to happen into the future is that the demand is going to increase 2 or 3 times in the next couple of decades. We're going to see many more electric vehicles, heat pumps, data centers, industrial processes, and carbon capture consuming electricity. The renewables will probably make the prices more volatile because we'll have times of very low prices and sometimes negative prices. But at the same time, when the renewables aren't functioning as well as we like, the prices will be quite high. And what we need to do is take advantage of this. This is a phenomena that until recently we haven't seen before, like negative prices and things like that. My feeling is that the economics and the reliability of the system shouldn't be separated. We pretty much leave those issues in separate buckets and let people work on them. But in fact, if you look carefully, reliability at its heart has an economic criteria. It turns out to be a combustion turbine, but and we'll get a little bit more into that as we go along. Reliability is going to demand greater regional coordination, especially in the extreme weather cases. But the good news is the extreme weather is much more predictable than the old N-1 criteria. You can see the weather coming and you can model things and hopefully prepare a lot better when you're dealing with extreme weather. And I noticed there's several presentations in this conference already that have started to deal with extreme weather, and that issue demands a lot more attention. We also probably need additional transmission if you're going to deal with extreme weather. Having the ability to move power over large geographic areas is very important. And consumers need to be more flexible. And they need to consume efficiently. Right now, as we'll see in a few slides, consumers basically are represented in most models as fixed points. And I noticed that that tradition is still true in most of the presentations that I've seen so far. Next, please. So FERC is doing quite a few things to move this process forward, maybe not fast enough, and maybe not as in much detail. 1920 sort of sets up a system, hopefully, that will get more transmission built. But the question of beneficiaries' pay still remains. Now, I haven't read cover to cover from the new the 1920 rule, but the fact of the matter is that it says very little about beneficiaries pay and how you model the system to get beneficiaries pay information out. And if you don't quantify these issues, in my opinion, the debate is going to be a qualitative debate that ends essentially nowhere. Next slide, please. Now, there's a whole bunch of words and phrases that I believe we should purge from our lexicon. 1 in 10, I was going to ask one of the presenters what one meant in one of the presentations this week, because he never defined what one was, but he used it as a standard to measure his system against. As I said a little bit earlier, the value of the lost load is the cost of a combustion turbine. That to most people wouldn't make any sense, but it's the standard procedure in electricity. And one of the things we don't know very well is what the true value of load is. And, you know, the estimates, when you look at the estimates that we use for the value of load, they're huge. And if you put them into the model, they would dominate the model. But on the other hand, we expect to see a lot of periods where the prices are going to be very low, and we would hope people would consume, but that information is not in these models for the consumers. to be dispatched accordingly. I won't go through the rest of these. If you tell load that they have to give up control of their processes, it freaks them out. And what the load should be doing is getting dispatch signals after they bid into the market. Next, please. Some phrases that we need to worry about from the ISO lexicon is market clearing price. We don't have market clearing prices. We don't have a single market clearing price, let's put it that way. Every ISO that I know has make-whole payments. And so if you look at the effective price that is being paid, the make-whole payments basically make everybody's, or a lot of prices different and discriminatory because they're getting the same service or commodity and they're paying a different price for it. So the argument that there is a market clearing price is a fallacious argument. And we need to understand that. Also, in the vertically integrated utilities, the theory is the consumers paid for everything, so we allocated the cost of this consumers immediately. In an ISO market, that is not the way things operate. That is to say, there are some consumers that benefit, some consumers that don't benefit. Sometimes generators benefit and not the consumers. So beneficiaries pay is a very important calculation, and we have to abandon the idea that consumers in the first instance have to pay for everything. Fixed demand modeling. If you look at fixed demand modeling from a purely mathematical point of view, it says that there's an infinite consumer surplus. That doesn't make a whole lot of sense, but in some sense, when you have a finite consumer surplus, a lot of the rules of thumb that we've used for years go out the window. We have learned to live with make-whole payments, and I don't think we need to, and we'll explain that a little bit later. Next, please. Next, please. So beneficiaries pay. Like I said before, this is an important construct, and the thing that we haven't done well is quantitatively model beneficiaries. And for the life of me, I don't know why we aren't spending more time dealing with that. Now, I noticed a lot of people are building a lot of models about, transmission and interregional transmission, but it's still not clear to me that we have a model that actually measures whether or not the system is beneficial and if it is beneficial, who are the beneficiaries? Recently, I noticed in the press that two senators from Kansas argued that the methodology from the SPP system wasn't correct and wasn't doing beneficiaries pay. And the commission responded, oh, yes, but they haven't changed the basic model that got the wrong answer. And if the model is to wait for the senators from the state to complain to FERC that it's not measuring the beneficiaries properly, that's not a good model. Also, it seems that FERC wants to allocate all the cost of a transmission line before it's built. It's really, over time, we've seen that people have built transmission lines and the beneficiaries they thought were going to be beneficiaries are no longer beneficiaries. The flow is different than it was predicted to be. And my feeling is that the idea that there's a once and for all allocation in and of itself is not clear. And that this the issue of cost allocation should be re-examined after actual operation of the system. Last but not least here, the formula rates that we use for transmission access have got to go. They're an artifact of a bygone system, and we need to actually rethink the way basic transmission rates work. Next, please. I will skip over this modeling. Next, please. Okay, what should ISOs do? They should essentially develop a new lexicon, a new set of vocabulary terms. They should promote bid and demand. And bid and demand, I think, is possibly one of the most important things that is missing from the ISO markets today. The question is, why? I've been studying this problem for several years, and I think I can answer the question, but it's a qualitative answer, not a quantitative answer, because bid and demand improves the overall market surplus. It improves reliability. And in order to promote bid and demand, we may have to re-examine some of the DR programs that exist today. The next thing to do is move to average incremental cost pricing, a methodology that was essentially developed here at FERC. And more research has been done since then. And as I said before, the reliability issue should switch to extreme weather reliability. Next, please. All right, bid and demand. Why don't we have it? Why aren't the large consumers, and by the way, we'll leave the small guys, for a discussion later. Why aren't the large consumers, and pretty much in the near future, we may see data centers that are 500 megawatts or larger. So, I mean, these guys are not your residential consumer, and there are many industrial processes that consume a lot of energy. And they could benefit by bidding into the market and by taking advantage of the times when the prices are low and having the ISO dispatch them away from the periods where the prices are high, which is what the ISO dispatch does. My research has essentially led me to believe that there's a lot of elasticity in the demand, and that it's demonstrated in the literature, and we should be able to capture it. We don't know how big it is, but one of the things we know is that, or at least I know from talking to people, that the large consumers don't really take participating in the electricity market seriously. And I think that's a big problem. And I think part of it is because they don't understand how to do it. We fed them DR programs, and it just literally does not make a lot of sense in some cases. And as a general rule, consumers need to be exposed to the wholesale price. Now, that's more of a political problem than anything else, but I think you can work on it. Next, please. Another interesting and positive property of bid and demand is if there's enough of it, the demand will set the scarcity price, and you don't need the ISO to be setting the operation reserves demand curve, which is essentially a scarcity price. And that means that the scarcity price is naturally occurring from the demand side bid when the system is scarce. Next, please. Now, this is the standard model that we all see in the textbooks where there's a downward sloping demand curve and an upward sloping supply curve with a Walrasian equilibrium. Now, a lot of textbooks don't say this, but this is a strictly convex market, which is essentially what we don't have. Next, please. Now, this is the picture that we have today, again, simplified. This is a vertical demand curve. The vertical demand curve produces an infinite market surplus or consumer surplus and market surplus. It has no flexibility. And I believe it essentially leads to inefficiencies in the market. Next, please. Now here, this is a busy slide, I apologize. But what we have here is that notice the black line has moved outside of the generator possibilities. It's beyond the, so what we do is we curtail demand. And let's say we curtail demand, what happens? Well, the price goes down. And we're talking about it, we're in a scarcity position. And if we had a demand curve, the red line up top, it would clear the market. Not the generator cost is not going to clear the market. The demand curve clears the market, and it sends a scarcity price to the system. It says there's not enough demand at this point in time, or not enough supply at this point in time, and you should consider building a generator. The green line, when you just simply shift this back, doesn't give that kind of information. Next, please. And this is just a clearing up the clutter from the previous slide. Next, please. All right. Average incremental cost pricing for markets with scale economies. Scale economies aren't going away anytime soon. We're probably going to have natural gas generators for the foreseeable future. And even if we develop carbon capture, those generators will still be available, but we'll still have scale economies. Now, in case you don't know what scale economies are, is that it's a system where the average incremental cost is declining. And that essentially, when there's a startup cost or a minimum operating cost, something like that, the natural thing is for the average incremental cost to decline. The average incremental cost pricing tends to be consistent with off-ISO trading, with the actual auction market dispatch itself. Because if you look at the decision of the mixed integer programming algorithm that solves the dispatch problem, it solves it based on the average incremental cost of the generator, not on the marginal cost. And consequently is more consistent with the overall system. It also is a better signal for entry and exit. And again, it is beneficiaries pay. And in these repeated markets, what you want the price to be is a signal for entry and exit, because without a decent signal, then you're probably not going to get it. Next, please. All right, let's, the simple thing is LMPs, ELMPs, convex hull prices are not market clearing. They all have make-whole payments involved, and consequently, they're calling them market clearing makes no sense. And all of the ISOs have moved away from what we would classically call LMP. And LMP pricing is now sort of a generic umbrella for what the ISOs do. Next, please. Now, this was a graph that was originally, I guess Alex isn't here, but it was developed by Alex, and and this is what the supply demand curve should look like. That is to say, you start up a generator, it has startup cost, and its average incremental cost go down over time and never get to its marginal cost. And so if you clear the market at the average incremental cost of the most expensive generator, there are no make-whole payments. If you clear the market, well, clear is the wrong word for marginal cost. There are make-whole payments. Next, please. This is just focusing in here. Next. Now, when you put in flexible demand, you introduce, I wouldn't say another problem, but a different issue, and that is to say that the average incremental cost price and the LMP price might be relevant. And probably I'd be glad to explain this to you, but it would take me more than my 5 minutes. Next, please. Next. Now, we've looked at average incremental cost on the system with 7 different MISO day-ahead dispatch markets. And if you see, this is a profit duration curve. If you notice at the very right-hand side, there's a bunch of blue dots that go below 0. That is to say, the LMP is not enough to cover the cost of the generators. But the red dots don't go below 0, meaning that the AIC model produces positive profits for all chosen generators. Next, please. This is just a blow up of the previous one. If you notice, the red dots are average incremental cost. The right-hand side of the red dots has 0 profits, which are I call incremental generators. The nice thing about it is that the prices are probably about 10% higher. Now, will the consumers see higher prices? I would say we don't know, because the prices that consumers see have about 20% capacity cost. And the way we do capacity, basically, if you raise the energy market prices, the capacity prices fall. If they don't fall, you've done something wrong. Next, please. This is just another diagram of what happens when you have a non-vertical demand curve, which is positive, but there are 2 clearing prices essentially, and I won't get into the details because there's not enough time. Next, please. Next. I won't go through these equations. Next. This is, I think, a very interesting example. There's 3 generators. One is out of the market at $206 a megawatt hour. One has a minimum and maximum that are the same, with a marginal cost of $53.10. And the optimal dispatch essentially dispatches generator 2. Notice it has a minimum run time of 4 hours. So you have to dispatch it in period 1, or period 1 to essentially for it to be available in 3 and 4 is when you need it. Next, please. the LMP in this case is $10 in all periods. It does not show the fact that the periods 3 and 4 especially, cause the startup and operation of generator 2. And both the average incremental cost and the convex hull in this case essentially allocate all of the costs of generator 2 to the period that caused the cost of the cost generator 2 to be operated or dispatched. It turns out that in this case, the LMP and the convex hull prices are exactly the same. Now, if I increase the maximum output of generator 2, the convex hull price declines and generates a make-whole payment. I don't see any reason why that should be the case because the dispatch is exactly the same. Next. Also, on the previous slide, you saw that $190 was both the AIC and the convex hull price, or the LIP is what it's called. And if it bids into, if generator 3 has a marginal cost of $190, it enters the market. And that's the correct signal that you got from the pricing in the previous slide. Next, please. It turns out that because of the complementarity of lowering the need for generator 2, you can have a cost of up to $206, and generator 3 will enter the market because you can get more generator 1, which costs $10 a megawatt hour. Next, please. And if you have bid and demand that allows demand to be shifted and some conservation, you can completely eliminate the need for generator 2. Without the bid and demand and the flexibility may be there, but we don't. It's not recognized in the dispatch model. So this is the selling point for bid and demand. Next, please. This is just this is a comparison of convex hull prices, ELMP, and AIC pricing. And this is obviously a constructed example, but they're very close to each other. They get very close to the same answers, except in several cases where the AIC ends up eliminating make-whole payments and the convex hull and the ELMP doesn't. Next, please. By the way, just as a side comment, the average incremental cost prices are much faster than any of the other or the equivalent when you're talking about ELMP. So there's no real computational burden in terms of getting this price. And just to summarize, no make-whole payments. Prices are probably 10% higher, but we know that capacity prices will be lower, so we don't know what the net effect is. I believe it's positive to have higher prices in the energy markets and lower prices in the capacity markets. And it sends better investment signals. Bid and demand essentially creates or eliminates the need for administratively determined scarcity prices and creates the scarcity prices in a crowdsourced manner if you have bid and demand. And one of the interesting things about having bid and demand is the two-sided markets. The dispatch algorithm finds complementarities that are very difficult to find without an algorithm for dispatch. It certainly is more reliable if you have the demand side in the market to shift and conserve instead of relying completely on the supply side of the market. There's been several presentations in here already where the demands, we're worried about reliability and we don't care about the demand side. Next, please. I'm just about done. This is a comparison between AIC pricing and CHP pricing. One of the things that everybody agrees on in convex hull pricing, implementing convex hull pricing, is that you don't let non-dispatch generators set the market price, which is what they do in convex hull pricing. Next, please. Questions?
Probably have time for one. Anyone has any?
Thank you for the great presentation. What is AIC pricing?
It's basically the simplest way of saying it is the average incremental cost.
Talking to the microphone for people to hear you.
Sorry. It is the average incremental price cost of the most expensive generator dispatched.
Okay, thank you.
Which is exactly the method. If you look at how the mixed integer programming algorithm solves the dispatch problem, that is exactly how it decides on the dispatch. It decides based on the average incremental cost, not the LMP, not the fixed cost or whatever. It is the proper match for the dispatch algorithm. Now, you add in bid and demand, and I think I showed you in this, it gets much more complicated, but you essentially increase the market surplus, which is something you want to do. Done?
Unfortunately, we need to move on, but the next presenter is also covering average incremental cost pricing, so.
Good. Oh, yeah. Well, good to see you.
Let's thank Dick. Thank you. And so we're going to move on to the next presentation. Manuel Garcia, average incremental cost pricing for the alternating current unit commitment problem. So just tell us when you want us to advance the slide and you're good to go.
Oh, testing, can you hear?
Yeah, Rob, could we turn it down a little bit?
I believe I'm sharing my screen. Can you see it?
Rob, or who's controlling the screen?
Yeah, it's Levon. If he wants to drive his own slides, that's fine.
Okay.
Okay.
Can you also just turn his mic down a little bit? Oh, okay, we're turning the speakers down. All right.
Hi. Yep. So hi, everyone. Yeah, thanks for introducing my topic, Dr. O'Neill. Yeah, this is a presentation that's based on a white paper that I just wrote with Dr. O'Neill. So on average incremental cost pricing for the AC unit commitment problem. So as we all know, the electricity market is designed around an economic dispatch problem that maximizes social welfare. And if this optimization problem is convex, if it were to be convex, then it would not only be easy to solve, but also it would be easy to compute marginal prices, and the marginal prices would satisfy a number of important market design goals. So those goals would include things like providing incentive to follow dispatch, making sure that all participants have the opportunity to realize a surplus. They provide efficient entry and exit price signals, and they also make it so that there are sufficient charges to cover payments so that you can ensure that the ISO won't realize a deficit. However, due to the nonlinear physics of the power system that need to be represented in these problems, this economic dispatch problem is going to be non-convex in practice, which makes it not only difficult to solve, but also if you could solve it optimally, there still generally won't exist prices that will satisfy the market design goals listed here. So the question then becomes, how do you choose the prices that at least approximately meet these goals? That's the question that average incremental cost pricing intends to address. The two most commonly studied non-convex economic dispatch problems are the unit commitment problem, which considers integer variables, and the ACOPF problem, which considers nonlinear transmission constraints. Both of these problems theoretically are NP hard. However, off-the-shelf algorithms tend to solve these problems very well. Now, up until relatively recently, very little work has focused on trying to solve the combined AC unit commitment problem. Recently, the ARPA-E Go competition has fueled quite a bit of work in this area. I think a couple of presentations after mine will be talking about different custom solvers that are capable of solving this AC unit commitment problem very well now. Due to that advancement in these solvers, I propose that we need to also focus on making sure that we have efficient market design and pricing design mechanisms available for the AC unit commitment problem, because the work in that area has also been lacking a little bit. Why not use LMPs or marginal prices? So for the unit commitment problem, their LMPs don't account for fixed costs or incremental costs, so that artificially kind of lowers the margin, the price, and causes some generators to realize a deficit. As a result, when that happens, as Dr. Neal said, make-whole payments are often provided by the ISO, but those have a lot of issues associated with them. For example, they're not transparent. Often they aren't disclosed to the public. They're discriminatory. They aren't covered by another revenue stream. And ultimately, they distort the entry and exit signals associated with the market, because it's difficult to predict what they will be. Now, associated with the ACOPF problem, there are other potential issues. An interesting issue has to do with if you introduce reactive power to the dispatch problem, then that theoretically implies that you should be also introducing a reactive power product into the electricity market. However, a common criticism of doing that is that marginal prices for reactive power are almost always very, very low. And that's because the direct cost of reactive power is very low, and the coupling in the transmission system between real and reactive power is very low. What we'll find here in this presentation is that incremental prices for reactive power may be large, making them more significant. So what is used in practice? So in practice, they don't price reactive power. But ISOs typically use LMPs coupled with make-whole payments. And some ISOs have small variations of locational marginal prices. So here I've listed relaxed minimum operating level pricing and extended locational marginal prices that I won't go into detail about, but they have the same effect, which is to sort of raise prices in a way that attempts to better represent the true cost of generation that accounts for incremental and fixed costs. Now, in the literature, there's quite a bit of work on minimum uplift pricing. Minimum uplift pricing is choosing prices to minimize uplift, which represents an inefficiency metric. So there are a number of different types of uplift. The most commonly used is side payments or make-whole payments. But there are also things like financial transmission right uplift that are a little bit more complicated. Now, convex hull prices are a special example of minimum uplift pricing that are sort of mathematically elegant. You can compute them as the Lagrange multipliers of a convex relaxation of the unit commitment problem. However, there are also quite a few criticisms of convex hull prices, and Richard O'Neill talked about them in his presentation. One that he didn't mention is that the assumed market structure in the convex hull pricing framework generally doesn't match super well with how markets are operated in practice. For example, they assume that side payments to generators cover lost opportunity costs when in fact they typically only are intended to make a generator whole. These are also prices that are generally difficult to compute. Average incremental cost pricing, there have been a few papers on this recently. So the average incremental cost of a generator intuitively is its cost divided by its output. Intuitively, if you set the price to be the highest average incremental cost generator, then there will be no need for make-whole payments because all generators will have non-negative profit. There are also a number of other benefits as well. Recently, Dick O'Neill has proposed this AIC one-pass pricing problem, which is framing, it's an efficient way of computing these AIC prices and frames these prices as the Lagrange multipliers of a slightly altered unit AC unit commitment problem, or not AC. He's only used DC in his work. So actually the work that I'm doing here is introducing alternating current transmission models into the AIC pricing problem. So in this presentation, I am really only providing an initial analysis of AIC pricing for the AC unit commitment problem. I'm not going to provide large examples or extensive results because I don't have them, but instead I'll provide some simple examples. I'll formulate a general one-pass pricing problem that is general, and then I will have a couple of profitability results that I included in a paper that I wrote. So here's the most simple formula example that I could think of. So here we have one bus, one time interval. We have real power only. We have two generators. One of them has high startup costs, generator 2, and since the locational marginal prices don't account for those startup costs, we see that generator 2 ends up realizing a deficit when the market is cleared, or I guess cleared might not be the right word. In contrast, when you use incremental prices, generator 2 is what we call the incremental generator. It sets the price to be its average incremental cost, and it breaks even. So that's sort of the intuition of how incremental cost prices are set. Of course, this is a super simple example. In order to, the computation becomes much more difficult when you start accounting for transmission constraints, time intervals, introduce reserve products or reactive power products. So for that reason, we propose solving a pricing problem that we formulate, which represents a variant of the AC unit commitment problem. So I tried to write this AC unit commitment problem as concisely as I could. So here we're just minimizing costs. The first two constraints represent the real power and the reactive power balance at each of the buses at each of the time intervals. The third constraint here represents generator private constraints. Of course, I've written them generally enough to where these can actually represent other things like flexible demand or potentially storage devices. And then we have the final constraint, which is the transmission constraint. And I've also written those constraints general enough to accommodate these nonlinear transmission constraints. So I'll be referring to the dispatch with this superscript star, and I'm only assuming that that is going to be a feasible dispatch. It's going to be feasible to this problem, not necessarily optimal. So the AIC pricing problem is a variant of that problem that is defined based on the dispatch that was chosen. So the first thing that we do is we relax the commitments to be continuous, and then we place a lower bound of 0 on the commitments and an upper bound of the dispatched commitment. So now there are no integer variables. The Lagrange multipliers are well defined, and that's how we define the prices, is through the Lagrange multipliers. We also add these constraints to E and to F. These constraints are a relaxed version of the equality constraints on the left. They're really intended to average the fixed costs over the real and reactive power. So here, X represents the commitments. So here we're averaging the commitment-related costs over the real and reactive power, which represent the products in the market. These constraints also encourage the solution of this problem to be equal to the dispatched value. That's not necessarily always true, particularly when there's flexible demand, but it often is true, is what we're finding in our results. I've also introduced an epsilon relaxation. So this sort of represents these two equality constraints as inequality constraints. And the reason for that is to improve a degeneracy issue that can result in having multiple prices. And I talk more about that in the paper if you're interested. Okay, so here I have a motivating example where a generator is committed specifically for providing reactive power support. So here we have a generator at bus 2, let's see. So the demand is located at bus 2, and the local generation also at bus 2 is expensive. Both startup and reactive power, or both startup and marginal costs for this generator are high. Then we also have at bus 1 a much cheaper generator. So the first thing to recognize is that the DC unit commitment problem would only commit generator 1 because it can't capture the voltage magnitude constraints. So that is the first problem to recognize. The second, so then also when we solve the AC unit commitment problem, instead we must commit generator 2, and generator 2 will only provide reactive power. So this is specifically to avoid dropping below the lower limit of the voltage magnitude at bus 2. And the real power output of generator 2 in this example is 0. So regarding prices, the first thing I'll point out is that reactive power prices, or reactive power must be priced in order for generator 2 to recover its costs. Since its real power output is 0, it can't recover costs by having a higher real power LMP. The second thing to notice is that the AIC prices must average not only over real power, but also over reactive power. If you only averaged the fixed costs over the real power, then you would find that the LMP for real power at bus 2 would increase to towards infinity because there would be a division by 0. So that's also a motivation to average the fixed costs over reactive power. A couple of other things that I'd point out on this example is that the locational marginal price for reactive power is 0. And that's consistent with what I mentioned earlier, where marginal prices for reactive power are almost always negligibly small. However, the incremental prices here are large, and they're actually large in a way that provides an improved pricing signal for investment, indicating that we need more reactive power support. So at this point, I'll provide some quick overview of these profitability results that I have. So an important claim of AIC pricing is that no side payments are necessary for generators to recover their costs, or that generators have non-negative profits. So I've shown that this is true under these assumptions, assuming that the generator satisfies each of these assumptions. So the first assumption here says that the generator is capable of not participating, so it can produce 0 output at 0 cost. The second assumption is stating that the dispatch value matches the solution of the pricing problem. And it's not necessarily clear that that should hold, but we do find that it typically does hold. I'll talk a little bit more about that in a couple of slides. And then the final assumption is that the prices are bounded, which is sort of a technical assumption. So this is the result that says that the generator's profits, if they satisfy those assumptions, will be non-negative. I've had to frame this results as a limit as epsilon goes to 0 because I was using the epsilon relaxation. So effectively, if you set epsilon small enough, then the profitability result holds. So then the question becomes, when does assumption 2 hold? When is the pricing problem solution equal to the dispatch? And I've been able to prove sufficient conditions for that, but they're fairly restrictive. I have them on this slide. It's beyond these fairly restrictive sufficient conditions, I will say that we've generally noticed that assumption 2 typically holds. But I do have some fairly restrictive assumptions here that say first that generation is positive, since I'm using a generator model that is also intended to accommodate flexible load. That means that there can't be any flexible load either. So that's fairly restrictive. And then assumption 5 here, which is saying it's sort of a generalization of a lossless assumption. It's saying that if you increase the generation at one node in the system, then you have to decrease it at another node in the system. So if these two things hold, then we can actually prove that all generators have positive profits. Let's see what time it is. So I have 2 quick examples that show about what happens when some of these assumptions are violated. The first example goes back to that 1 bus real power example that I showed earlier. So here I've changed the generator 1's startup or initial startup condition, and also reduced the load. So in this example, generator 1 wants to turn off, but it can't. So that violates assumption 1, which states that a generator has to be able to not participate. So in that example, you see that the generator does realize a deficit, even though the profits even though we use incremental prices. Of course, this is also a problem with LMPs, but it's important to recognize that if you just run the unit commitment problem and use AIC prices, that occasionally you will find things like this where it makes sense that the generator wouldn't be able to recover its profits. And then the final example I have here is illustrating what happens when we introduce flexible demand. So I've introduced flexible demand actually as a generator that has a negative output. So in this example, we're violating that assumption that is that all generators' outputs are positive. And indeed, we find in this example that the solution to the pricing problem doesn't match the dispatch, and as a result, the generator that doesn't satisfy that that assumption or the flexible demand that I've introduced has negative profits, and that is related to the issue that Dr. O'Neill was talking about at the end of his last presentation related to flexible demand. So that's a topic that I think warrants future research. Now for future work, I'd like to just generally encourage more pricing related research in the topic of or in the context of the AC unit commitment problem. For this work, I need to do more large-scale computational results with the AIC pricing problem. That's important. Another one is to sort of make the problems more detailed and accurate. I don't include reserve in the work I presented here. So how do you account for averaging fixed costs over reserve products? That's something that I believe should be done, but I haven't looked at that yet. Let's see, there are a couple of others. One that I will mention is that occasionally there are multiple optimal AIC prices. In particular, when a generator is committed at a time interval that is earlier than when it needs to be committed, you can run into a problem where it's not super clear whether or not you should allocate the commitment costs to the interval it's committed in or a different interval. For example, the interval of the peak demand. And that's also something that Dick talked about in the last presentation. But it is important to sort of understand or characterize the set of possible AIC prices, and then ultimately choose which AIC price best matches our market design goals. So with that, I'll leave it open for questions.
Thanks, Manuel. I don't know if you can hear, but we're clapping in the room. Does anyone have any questions? Okay, one second.
Oh, I'm Inoto. Thank you for your presentation. And I think you mentioned the financial transmission uplift related papers, and when it comes to the FTR uplift, convex hull pricing related to or cause the FTR uplift. So, and Dr. O'Neill's paper uses the convex hull pricing related method to solve the AIC pricing, I think. So the FTR uplift phenomenon would be caused by ACOPF method, I think. So did you is the phenomenon happens in the two-bus model? Excuse me.
Yeah, thanks. Yeah, so so regarding FTR uplift intuitively is kind of complicated. It sort of represents the worst case possible shortfall of congestion revenue when after you pay off the generators and receive payments from demand. Now, the real issue of concern when it comes to congestion revenue adequacy is what happens when there are transmission line outages or transmission switches, because oftentimes FTR auctions don't really consider these switched states of the transmission network. So that's the primary issue when it comes to financial transmission right congestion revenue adequacy. There is a theoretical result regarding congestion revenue adequacy and FTR uplift for the ACOPF problem that states that it's possible for there to be congestion revenue shortfall in the context of financial transmission rights if you use any pricing scheme, the convex hull pricing or the LMP pricing. I haven't seen AIC pricing results on this yet, but I think the consensus among people that I've talked to is that it's not really a super big issue because the real issue when it comes to congestion revenue adequacy is transmission switching and line outages. So yeah, thanks. Thank you though.
All right. Thank you again, Manuel. We can give him another round of applause. That's fine. Thanks, Manuel. Okay, next we have Farhad Haider, deep learning-based transmission line screening for unit commitment. Is that all right?
Hello. Hello.
Okay.
Okay. Hello, everyone. I'm Farhan. I'm representing Rochester Institute of Technology today. And this is one of our ongoing works on transmission line screening for unit commitment. Next. This is just the outline of the work. I'll go over the motivation and ideas why we are doing this, then methodology, and then the results. Next. So what is the motivation for this? We know that with several hundreds of thousands of transmission constraints, the complexity of the unit commitment problem is pretty high. And a lot of these constraints, a lot of these transmission lines are unlikely to be congested or not loaded much at all. And filtering out such constraints could reduce the computational complexity of the problem. The difficulty is if you remove too many constraints, the problem becomes infeasible. And if you remove too few constraints, the computational performance might not improve that much. Next. We looked into the literature on this. There's two classes of approaches. One is a traditional approach where it guarantees solution feasibility, but computational performance is usually not great. A common method is to generate constraints and iteratively add constraints to see until there are no violations. Another approach is to minimize and maximize the flow through a given line to determine if it is likely to get congested or not. In recent times, there have been some machine learning approaches that offer better computational performance, but can cause infeasibilities. And their methodology is also based on if the line will be congested or not. Some people have used k-nearest neighbors recently, and they have tried neural networks, but the problem is with infeasibilities. Next. So what we noticed is just like how demand is in the future is dependent on demand in the past, future line loading might depend on nodal demand and line loading in the past. And if we if we capture such a temporal relationship, it might help us avoid infeasibilities. So we developed this model called the regression-based classification method. The idea is to capture these temporal relationships between past nodal demands, past line loading levels to predict future line loading levels, and then classify the constraints as necessary or not necessary. for the UC problem. We believe if we do take such an approach, we might be able to improve computational performance while maintaining solution feasibility. Next.
The slides are controlled in that box, so you need to speak into the mic.
Okay. So since the emphasis is on identifying the set of transmission line constraints that can be safely removed, we use a simplified version of the UC problem, where we have taken out a lot of constraints that might affect transmission lines in ways which will make it hard to decide which line is make it difficult for our methodology to understand why transmission lines are getting congested. So in the simplified formulation, we only have the generation cost, balance condition, generator limits, and the transmission network constraints. Next. So what do we do? So the idea is to decide every line for every R should be classified as necessary or not necessary, which is like a label 1 or label 0, for which we consider 3 input-output configurations. One is to just use past nodal demand to predict future line loading. The other one would be only using past line loading to predict future line loading. And then you combine both past nodal demand and past line loading to predict future line loading. And the way we define future line loading is just the absolute value of the flow divided by the maximum amount that can flow through a line. The idea is to pick the best configuration for screening redundant constraints. Next.
Again.
Okay. Okay, understood. So we first use a LSTM model for regression that predicts just the line loading value between 0 and 1. And then we use a threshold-based classifier to decide whether to keep it or not. So the idea is once you train the model, you don't have to train it again. You can just use different thresholds to determine up to what loading you want to keep. Like, for example, if you want to decide that anything loaded less than 50% can be removed from the problem, you can just set the threshold to be 0.5. And like that, depending on the volatility or the sensitivity of your grid, you can set a higher threshold or a lower threshold. This just shows, the figure here shows the network we used, which 2 LSTM layers and 3 fully connected layers, and some of the hyperparameters. The important thing to notice here is that the time step, we looked at previous 8 days to predict for the 9th day. That is, if you want to predict it for a Tuesday, we look at from this Monday to the past Monday. So we look at 8 days to predict the 9th day so that our model learns not only the daily fluctuation, the daily curve, demand curve, also the differences between weekday and weekends. Next. Okay, so for the data preparation, in the results section, we took the IEEE RTS 96 system. It has 120 lines and 73 nodes. We took historical data for 365 days, ran the simplified model to get line loading levels. Then we took an interesting approach to dividing our data into training and testing. So since there are seasonal variations, we divided our data into 4 quarters of 90 days each. And within each quarter, we use 80% of the data for training and the rest for testing. And for comparing each configuration, we use mean square error and classification accuracy. Next. So this is what the results from using the 3 different configurations, where here the best results we got were for combining past nodal demand and past line loading levels to predict future line loading levels. Gave us the best results in terms of regression, and for almost every threshold as well, we got the best accuracy with this configuration. So we decided to use the X5 to Y hat configuration for the regression-based classification method. Next. Okay, so for testing it on the unit commitment problem, since it was a simplified problem, we combined several days. So we tested the entire quarter at once so that we have a significant number of network constraints which will help us analyze the problem with around 51,000. To compare, we used a solving time metric, a difference in cost, number of constraint violations, and compared it to a full network considering all network constraints were there. A simple example of a single bus network where we are not considering any network constraints. Historical analysis where we would only retain lines that have never been congested in historical data, ignore the rest. What we aim to do is we want to understand the impact of transmission line screening on solving time, constraint violations, and solution quality. I'm going to present the results for Q1. Rest are available in our paper. Thank you. Next. Okay, so first is the impact on transmission screening on solving time and constraint violations. So the orange curve represents constraint violations, while the blue one represents solving time. And as expected, for the full network, there are no constraint violations, and it also takes the highest amount of time. And single bus is the exact opposite because you're not considering any constraints. Historical analysis, which is just looking at in the past if they were ever congested, gives high number of constraint violations. And then we use our approach with different threshold values. Here, 0.4 means any line that is loaded less than 0.4, that is less than 40%. For that given hour on that particular day, then we remove it. And for a different hour, if it is loaded more than 0.4, then we keep it, put it back. So it's like a switching system, like a 0-1 matrix that decides for which hour, which lines are considered. So we noticed that up to threshold of 60%, there were no constraint violations at all. But at 70%, there were a few constraint violations, which we were able to remove using constraint generation. But that shows that the approach can reduce solving time significantly while not having constraint violations until a threshold of 0.7. Until 0.6, there were no constraint violations. 0.7, there were a few. And depending on the amount of fluctuations in the demand, we could be even more conservative with our thresholds. Next. This is just a quick glance on the solution quality, also which shows the number of percentage of constraints removed. With our approach, we were able to notice that even with up to 76% constraints removed, solution quality was fairly same. There was no meaningful difference between the solution quality. For 0.7 case, because there were a few violations, the solution quality was bad. So we thought what we can do about this. And we came up with a time-based approach. Next. So we decided to have time-varying thresholds so that after we do our threshold screening, we added an extra layer where transmission lines are given a different threshold based on whether it's during peak hours or during off-peak hours, since the expectation is the lines are more likely to be loaded during peak hours. So for this small example, we used same threshold for both peak and off peak 0.7. And then we tried with a different threshold of 0.6 for peak, but off peak remained at 0.7. So we noticed that the number of violations came down significantly, showing that using a time-based approach where we have a different threshold for off peak and peak could be beneficial. Next. So in conclusion, what we understand is we used a simple time series network like an LSTM to get the predicted line loading levels. This, when you're operating a grid, you probably won't need this because you will have the actual data from your day-ahead model that will give you the line loading levels. Then the idea is to just use a threshold-based classifier to classify constraints based on how up to what percentage they are loaded. And our results on the RTS96 system showed that there were no violations up to 0.6. And if we have different thresholds for peak and off-peak hours, the violations can be reduced further. Overall, there's some promise in this approach, but a lot more work has to be done in the future. Next. So for the future approach, we want to try a UC problem with intertemporal constraints since we use a simplified UC model to understand the impact of transmission constraints. That was good enough, but we need to incorporate intertemporal constraints to make it more practical. And then examine the approach on larger scale networks. RTS96 only has 120 lines. We want to try it on systems with 2,000, 3,000 transmission lines. And with the LSTM approach for the machine learning, we are only capturing the temporal information. So moving forward, we would like to capture the spatial information as well, something for which we are considering temporal graph networks, which would look like the figure here. At T, we'll have certain number of features for the node and edge. And at T+1, the features would change. So this way, we are capturing the grid through a neat graphical network. And we are also looking at it for different time frames, which might help us understanding and learning the grid better. Next. Just some references next. Yep. So we published this at last year's PES, and more detailed results and descriptions are available in that paper. But it is one of the works we are extending to larger networks to see how it would work on more practical size networks. Thank you.
Very much. Any questions?
Hello, my name is Alison from Argonne National Lab. Thanks for the talk. So as you mentioned at the beginning, there have already been a number of works working on transmission line screening, some of them based on machine learning methods, and some of them already handle large-scale networks and even the security constraint and commitment problem. So I'm just wondering whether you compare to these previous approaches, and if not, why not?
Not yet, but it is something I'm planning to compare. In this work, I was for a conference paper. We didn't get enough time to do the comparison with other methods, but that's something I'm planning to do.
Okay, thank you.
Hi, I believe we have an online question.
Okay.
Oren, I'm going to ask you to unmute.
Sorry, this was for the previous talk, so.
Sorry, can you speak up?
My question was for the previous talk.
Oh, apologies. Sorry.
We could pass it along to the author. If he's, I'm not sure he's still on. Anything else for Farhan? Okay, thank you so much. All right, next is I believe a virtual presenter, Andy Sun. Recent advances in solving large-scale security-constrained unit commitment ACOPF. You're sharing your screen, I believe.
Yes. Hello.
Okay.
Can you hear me?
Yes, we can hear you.
Loud and clear.
Great. Thank you very much. Really been enjoying this conference. My name is Andy Sun. I'm a professor in operation research at MIT Sloan School. So I will present some of our recent work on solving the security constrained unit commitment ACOPF with line switching. And also thank you for the previous presenters of their excellent work, which also sort of motivate and outline the scope of sort of research in this area, the various challenging questions involved. So let me see if I can move forward.
Oh, I'm sorry. Did you want to drive your slides?
Yeah, if I could.
Okay, sorry. 1 second.
Okay.
Just go ahead and share when you're ready.
Okay. This one. Let's go.
Thank you, Levon.
Let's go back. Okay, let's try. Okay, great. So there are many challenges facing the decarbonization of power systems, from long-term planning of how to reach a zero-emission power grid to operational problems of how to operate large-scale power systems under increasing uncertainty. and to market challenges, as the previous speakers have excellently outlined, of the challenges of pricing electricity and also resource adequacy, and also adaptation of how to deal with increasing coupling of related infrastructures, including power and transportation and buildings and so on. So if we look at this from a operations research optimization lens, I could see several intertwined challenges from optimization perspective, such as solving large-scale non-convex optimization, which AC OPF plus unit commitment is sort of a very important example of this. Not only how to solve it reliably and effectively to get feasible solution with high quality, but also how to price the mixed integer nonlinear program, which is exactly the pricing problem. So you can think about this as, on the primal side, we have challenges of actually getting primal feasible solution with high quality, and on the dual side, understanding how the prices get affected by the AC system with unit commitment and other non-convexity. And also another aspect is optimization and uncertainty when we have a lot of renewables and also new types of demand that represent increasing uncertainty. How to model them is a challenging question, especially in large system in a market. And also how to coordinate a lot of diverse agents effectively, centralized or decentralized way is also quite challenging from an optimization perspective. So all these areas have challenging optimization problems that are also intertwined into a problem that, you deal with one problem, you probably have to consider other aspects of the challenges. So I'm going to talk more about the first challenge here in this talk, about solving high fidelity power grid optimization models. As I mentioned, there are primal side of this challenge of obtaining high quality feasible solutions, and also dual side, which is about providing strong convex relaxations of lower bound and also pricing. And I would like to, in the end, reflect or think about, or really make the audience think about, are we reaching or getting closer to a tipping point in terms of, if you think about the landscape of software being used in ISO RTO environment, are we closer or getting close to move toward implementing AC? Because that really depends on a lot of the research advances, both in academia and industry in the past several years. And AC OPF and unit commitment is sort of a core problem that's permeated in many different problems or tasks facing operating planning of the power grid. So I think everyone is very familiar with the ISO market. For example, day-ahead electricity market, where the ISOs solved a unit commitment problem about half a day before the real-time operation. And here, most or all the ISOs use some kind of approximation of the power flow, AC power flow, especially DC OPF approximations. And in the real time, this is taken from the PowerGEM market. In real time, a sequence of optimization problems are solved, especially when we get very close, say 10 minutes before the target time of operation. A real-time dispatch problem is solved, which has, in this setting, 4 time periods of increasing time length from 15 minutes to about 2 hours. So this multi-period economic dispatch problem is solved in about 10 minutes before that real-time operation. And again, this problem is formulated as a DC OPF with various simplifications for computational purpose. So FERC has this vision 18 years ago, almost 20 years ago, of looking at what will be the next step. So at the time, DC power flow based algorithms are used as for now also. And the question about switching to AC based software is challenging, and it was challenging, and it's also challenging today. in particular, the computational capability of solving such problem, AC problem, and not only solving them effectively, but also in very stringent time framework, and also requirement of high reliability of getting solutions, of getting high quality solutions. So, but FERC has put a lot of, I think, leadership and guidelines in terms of moving forward toward a AC-based security constraint OPF, now also with unit commitment. So a lot of advances have been happened in this area in terms of solving unit commitment problem with DC OPF approximation, to solve AC OPF problem with sort of fixed UC solution, both in the primal side of things and also in the dual side of providing convex relaxation that is both very strong and also very computational efficient, as well as the combination, some work, not very extensive, but some work in UC AC OPF using generalized benders, for example, and looking at global optimal solutions using convex relaxation and branch and bound based on the current previous work or recent work on convex relaxation of AC OPF, as well as optimal switching problem. I think all of these problems are being investigated quite extensively. However, up to now, I think it's still quite challenging to solve this combined problem of UC, AC with a use security constraint and also switching in the current ISO TSO market. So I would like to say a big thank you to ARPA-E and DOE for actually organizing it's first of its kind competition on grid optimization. And I think Dr. Dick O'Neill played a prominent role here for guiding this competition and encouraging the participants to work very hard on this. I think this competition in the 3 phases since 2019 have been really instrumental in fueling the research in this area and pushing, the boundary of computational capability forward. So I think some of you probably are quite familiar with this challenges. So just very briefly, an outline of what has been modeled in these 3 challenges. I think it's kind of well-defined, well-designed progression of complexity of the model from challenge 1 to challenge 3. So challenge 1 is basically a single period AC OPF problem with some very interesting twists. For example, PV PQ switching in base and contingencies and AC preventive and corrective agent contingency actions and a lot of contingencies. So at that time, the problem already, the scale in terms of scale is up to 30,000 buses and 35,000 branches. The goal is to solve such problem to get truly highly feasible solution in 10 to 45 minutes. So it's very much a sort of a real-time market-oriented single period AC OPF problem. The second challenge moved forward. In addition to the single period AC OPF, now a single period UC decision or UC problem is added, both in the base case and in contingencies. And also flexible load can be dispatched, and branch switching, shunt switching, tap ratio changes, and angle changes of transformers are all included. So this already had the elements of mixed integer variables in the UC decisions, as well as non-convex, continuous non-convex constraints from AC power flow. So what is challenge 3? Well, the challenge 3 is even more challenging. So we have this team of excellent graduate student and postdoc working together. As you see on the left, this picture of 5 people stacked up to repair a line. I think building a very, very effective, reliable software for solving this UC, AC, and line switching problem is quite challenging. It's a team effort. So the challenge 3 is a extension of challenge 2 from single period to multiple periods. I think that's sort of a one-line summary of what challenge 3 is. But the true complete model takes 60 pages of documentation with 320 equations. The key features are a full UC set of constraints, which linked devices through multiple time period, and ramping constraints, also linking time periods, and AC power flows that link spatial different nodes together through AC power flows. And then there are quite a set of comprehensive reserve constraints, both on the unit level of real power and reactive power reserves, as well as zonal reserve requirements. So it couples also locations through reserve constraints. Also, there's some storage constraints, for example, maximum energy over a time period. So that could model some kind of storage in the network. And prosumers, so generators and consumers are sort of on an equal footing of their capability of being dispatched and decisions being made in dispatching them. So so there's a more sort of summary of this multi-period security constraint UC ACOPF with line switching. So when we started solving this problem, I think it's fair to say that the existing software out there that we could have access to really couldn't handle such a problem in large scale. Remember, we could probably solve a 3-bus system with a full set of constraint of this problem over multiple time periods, and all these reserves, line switching, and so on. So it's really quite challenging. And the goal is to develop customized software or solvers that could solve such a problem up to the size of problem or network that I think is comparable to US continent power grid. For example, West interconnection is roughly the size of their high voltage network. Eastern interconnection is bigger, it's maybe double or triple the size, but depends on the voltage level we're talking about. So we could select certain level of voltage where the size of the network is on the similar order of magnitude. So the point is, in terms of the size of the problem, I think this competition really push it up to the size that is comparable to not only one ISO, but maybe several ISOs in a large geographic region. In terms of the computation time, so there's 3 different problems, essentially. One is 10 minutes problem where you solve very much similar to what I showed in the PJM market, that look-ahead problem 10 minutes ahead of the operation time. And then there's a 2-hour problem, meaning you solve the problem in 2 hours, and that problem is a day-ahead problem. And then there is a weekly planning problem that need to be solved in 4 hours. So what is the structure of this challenge 3 problem? I think essentially is a spatial temporal coupled system where in each time period, we have a power grid that couples spatial variables in terms of AC power flow reserves, for example, that lived in different nodes with their decisions, but they're coupled through this non-convex set of non-convex constraints. And then each time period, the network structure could change. It's a control variable that you could change the structure or topology of the grid. And over time, there are also temporal couplings. These are, for example, UC constraints or storage constraints or ramping constraints that couple devices through time periods. Okay, so by this coupling structure, you already can kind of see that it's kind of a product of 2 types of couplings, the spatial coupling and the temporal coupling. And that's challenging to handle if they are all entangled in this way. So not only spatial and temporal coupling, but also there's a 2-stage coupling. As we know, there's a base case and then there's contingencies. as the previous talk focused on, how to actually screening contingencies and picking out the right ones are actually very, very important. So, so there's kind of 3 different types of coupling to inherent in this large scale problem. And in terms of computation time, I think the real time 10 minutes is actually quite stringent. But when we move to day ahead and planning problems, the computation time is 2 hours and 4 hours is much longer, but also the problem actually is larger. In terms of the memory constraint, I think the competition has about 200 gigabyte of memory, and it's actually quite tight for solving that largest system, the 23,000 bus system. The problem size is actually quite large, considering all the variables, both in base case contingencies. It could be up to 50 million variables. So solving this problem definitely is challenging. And our strategy is to exploit this structures of spatial, temporal, and 2-stage coupling and try to decompose problems along these lines. So we developed some tailored spatial temporal decomposition algorithms, and that is an iterative procedure that decoupled the unit commitment problem from the AC power flow problem. And we also used some recent developed strong convex relaxation we built a relaxed convex relaxation of the entire problem so that we could basically measure the solution quality of our primal feasible solution. And not only that, the convex relaxation turns out to be very critical in speeding up the spatial temporal decomposition algorithm. And we also developed some convex restriction approaches to deal with, for example, temporal coupling, the ramping constraint. If we completely ignore the ramping constraint by relaxing them, then the solution, of course, may not actually satisfy those temporal coupling constraint, and that could lead to constraint violations. So bringing them back into the problem is very important, but we also want to make sure that they don't couple the temporal periods. So we developed some convex restrictions constraints such that it could, by solving decoupled problems, we could guarantee feasibility for temporal constraints. And here is just a cartoon illustration of this overall spatial temporal coupling or decomposition approach, where we decompose spatially the unit commitment constraints into different devices through time periods. And then there is a decomposition of the AC multi-period AC power flow into single period AC power flows. And there's iterative process of solving this problem. And then there is a final AC OPF solve to get a high quality feasible AC solution in the end. So in terms of the test system, so the PNL team and the Go competition administration team really put a lot of effort in developing a set of quite comprehensive test cases, both with synthetic power grid and also industry power grid. So here it's shown the number of buses to illustrate the size of the scale of the problem, from a very simple small 3-bus system up to 23,000 bus system. And the industry case is about 6,000 bus. We don't know exactly what that system is, but it's 6,000 buses. And in terms of number of periods, as I mentioned, there is a 10-minute division, meaning you solve the problem in 10 minutes. And that problem is a multi-period, sort of real-time multi-period dispatch problem with 8-hour horizon. And the time interval is from small, 15 minutes, up to 1 hour. That's quite similar to what we see in the PJM market, in the real-time market. And then there is a 48 time period model for the day ahead, or 2 days ahead. problem that need to be solved in 2 hours. And then there's a 42-period model of about a week's time horizon that need to be solved in 4 hours. So as I mentioned, if we compare the size of the system to the real-world power grids, we see that these are some rough numbers for this 3 power grid, ISO New England, or Western interconnection, or Eastern interconnection. Again, the number of buses depend on the voltage level that we look at. I think above this 70,000 bus, for example, really includes sub-transmission voltage levels. So if we really look at high voltage levels, this number could be actually much smaller and closer to the 23,000 bus system. Okay, so in terms of the computational performance.
Sorry to interrupt. I just wanted to let you know you have 3 minutes left.
Okay, great. Yeah, almost done. So this is a slide about the computational performance. There's very comprehensive tests in 4 events of the code on all those 600, more than 600 test instances. So what I show here is for all the test instant cases, we can solve almost all of them in the time limit in the 3 different divisions. The thing that I want to highlight is we can also measure the solution quality of our problem, of our solutions. In particular, because we have developed this convex relaxation of the whole problem, so we can compare that lower bound to our solution, primal feasible solution. And it turns out that the average optimality gap is about 0.6% with a standard deviation of 2%. So this is over more than 600 test instances. It shows that the primal feasible solution is not only feasible, but actually very, very close to global optimal solution. And so that's encouraging to show that the solution, even though we're not using global optimization, is actually quite good. Okay, so I think there are many practical implications here in terms of where the models really kind of match the current ISO, TSO market setting in both their models and also the size, the scale, both temporal and spatial scales. And code seemed to be quite robust in solving these problems in the very stringent time limit and I think appropriate software and hardware requirement, environment requirement. And to reflect on this, I think it's very important to have a systematic strategy of developing algorithm of solving such a problem. And every single little piece matters in terms of getting really good solutions. There are also future challenges in terms of uncertainty, pricing, down to distribution grids. And I just want to mention this tipping point thoughts. Are we getting close? I think AC power flow or AC problem definitely is much more challenging to solve, is much more complex to understand. But there is a quote in mathematics: "We don't understand things; we just get used to them." You may guess who said this. Maybe a very, very stressed undergrad student learning mathematics. But actually, this is the great John von Neumann. The point that I want to make here is the problem is intrinsically complex. It is a complex, complicated problem. Of course, it's our job to try to solve it and try to understand it well. But in the end of the day, it is more complex than what we have in the current market. But it may be crucial to move toward that direction and to gradually get familiar and understand things. So in terms of the progress, I think I see slow but accelerating progress toward solving this problem, starting especially in the early 2000s, the adoption of MIF solvers. I think that's a great step moving forward. But 20 years later now, I think we are moving toward increasing capability and maybe moving toward including AC-based software in the ISO, TSO, RTO setting. So here's some papers if you're interested. Here's my contact information. Love to hear any questions, discussion. Thank you.
Thank you, Andy. Do
Thank you.
we have any questions? Anything online? Going once, going twice. All right. Thanks again, Andy. All right, and our last presentation of the day is from Jesse Holzer. Jesse Holzer online, and he will be presenting from AC unit commitment in the grid optimization competition challenge 3. So hey Jesse, we can see you. Maybe just do a quick mic check.
Hello.
Yep, we can hear you.
Very good.
And Levon, I think we'll just say next slide when you're ready for the next slide.
Okay.
Or would you rather control it?
I think I'd rather do it if that's all right.
All right, Levon, I think not just share your screen.
Yep.
Thanks, Levon. Okay, go
Does
ahead.
that look right?
Yep. Thanks.
Okay. And okay, I'll just go ahead. So I'm Jesse Holzer. I'm a mathematician at the Pacific Northwest National Lab. I've changed my talk title and content somewhat. So this is going to be a sort of a retrospective look back at the grid optimization competition. So this slide shows as much as I could get in of the team that put on the Go competition. So this is really the administrators and sponsors, and it's been an amazing an amazing project. So this project has gone for 8 years that I've been involved, and it was getting spun up a couple of years before that. The Go competition is ending in terms of the work that it will be doing. So I thought that this would be a good opportunity to review sort of some greatest hits. At this point, I'd like to give a big thank you to some of the people. So especially the program directors at ARPA-E, Tim Heidel, Corey Hedman, and Dick O'Neill. So this project we had weekly and sometimes bi-weekly meetings with our program directors. I think that that's kind of unusual in a Department of Energy funded project. It was that close relationship with our sponsor was absolutely crucial to doing a good job on this project. So thank you, Tim. Thank you, Corey. Thank you, Dick. And I also want to give a thank you to Steve Elbert, who was the principal investigator and PNNL person. So Steve has led this team through many changes, and what a great job he's done, keeping us in line and making sure that we get everything done in a timely fashion. So let's go ahead. Oh, and by all means, please check out the webpage listed here, Go Competition. Okay, so what I want to talk about today is some big picture stuff about the problem that we were out to address through the competition, and the approach that we used. What makes the competition approach unique, I think, is what I want to get at there. give some highlights of success stories. And for my own experience in the competition, I did a lot of work on writing down the model and understanding what we were trying to do. So that's something that I'll highlight here is just some of the unique-ish model features that we put in and what we were thinking, why we wanted to do it that way. So to lay the scene for the problem, imagine a sort of highly accurate and detailed model for wholesale electricity markets and operational planning. So a model that sort of combines a lot of the things that the computational engines in wholesale electricity markets currently do separately. So I'm thinking combining unit commitment, AC optimal power flow, transmission switching, all with a network model that's extremely highly detailed. You might call this a super model. For today, I'm going to call it a Go style model. So with this Go style model, the basic idea when you have an optimization model that puts in all the details is that you're trying to get more value, more efficiency out of what you're modeling. So just to get more out of the installed grid equipment. Of course, that greater accuracy and detail that comes along with computational complexity. And so it makes it more difficult to solve. And that's really been the main case against a model like this. Up till now, I would say solvers for a model like this were not mature. And without a mature solver, the industry players don't really want to use a model like this. It's risky and maybe won't work. So getting the solver development really was the big problem. So our approach to this, our approach to moving the solver needle, it is to, well, I guess I would say to spur research and development for solvers. So as the previous speaker outlined, we have posed 3 challenge problems. And for each challenge, we created data sets, specified the problem formulation in exhaustive detail, and created a common platform for solvers to run on, and wrote code to evaluate solutions. We built a benchmark solver for each of these challenge problems, and we invited solvers to compete on them. The goal of all this was to attract really diverse ideas and approaches and areas of expertise, right? To get the software developers and the engineers and the mathematicians and the economists and the power systems specialists and the operations research specialists all together on one team, and then to get multiple teams that would have different strengths, all trying to solve the same problem. Essentially, we built a level playing field for these different teams, and I think that's part of the uniqueness of the Go competition approach. When I think of maybe a traditional research project, you can sort of design the problem that you're solving to highlight the strengths of the approach that you're interested in pursuing. With the competition, we definitely prevented that. So there's one problem, and the solvers get to concentrate on building the solver, building the algorithm to meet the problem, rather than reverse. So the separation of the development of solvers from the creation of the problem, I think, is a key feature of this competition approach. As as has been mentioned in some of the previous presentations, we got some very large data sets out of this. This was actually a pretty challenging effort creating these data sets, and essentially a project in itself. Some of that is synthetic data sets, but we also were able to build in real data from commercial partners. And so part of the uniqueness, again, of the approach that we followed was that we were able to maintain confidentiality of the commercial data. And basically the way that this was done was that we ensured that all of the solver runs on data that had any dimension of confidentiality to it were done on our own hardware. So it never left the building at PNNL. I think that the biggest successes really are the solvers themselves. So I want to take this opportunity now to offer congratulations to the many successful solvers and the teams that built them, and the individual researchers that contributed. So Go NLP from Livermore was a highly successful solver in Challenge 1. Pearl Street, Gravity X is an individual, Hassan Hijazi. The GOT-BSI OPF team, GMI Go from Georgia Tech, Tim Go from MIT, and that was Dr. Sun, who just spoke. The GoSNP solver from Lehigh, and I definitely want to mention the successful solver that the Go competition itself built, the RPE benchmark solver. And this was led by the Los Alamos team with Carlton Coffrin. Young Optimization at Mississippi State built a very successful solver in Challenge 3. Northwestern University, Columbia, and Martellus, and the Blackouts from University of Tennessee. And so these are not all of the teams. These are, and maybe I even missed some that were quite successful, but these are the ones that I jumped out to me as highly successful solvers. Another important way to think about success of this project overall is that the Go competition has been cited by many publications already. And you can see this on our webpage here. And I think the sort of enduring legacy of this project will be the influence that we've brought on really a whole cohort of researchers in this field. Not to say a generation, but maybe a cohort, right? So a decade's worth of researchers have joined in this effort and have established lines of research supporting this. So I hope to see the sort of results of that influence in coming years as these lines of research become mature. Okay, so now we'll talk a bit about some of the formulation ideas. So to sort of lay the basic groundwork, I want to briefly talk about why we want to use AC optimal power flow. And I think a key consideration here is the idea of stressed grid conditions. So what that means is sort of the line flows closer to their limits, larger voltage angle differences, voltages further from nominal. These conditions imply that the DC approximation is more inaccurate, or really any linearization is going to be more inaccurate. I guess I'm making a hypothesis here that under these stressed conditions also we have sort of more non-convex difficulty of the AC optimal power flow problem. That's maybe a challenging statement to make because sort of in a general sense, AC optimal power flow, while it's algebraically non-convex, tends to have relatively few serious local optima. So that typically a local optimization method winds up finding maybe a global solution. But this is a hypothesis that anyway I'd like to explore at some point on what happens with stressed conditions. But so if we don't use an AC optimal power flow model, and we're using a less accurate DC model, well, I guess I would think about a picture like this. So maybe we have line limits, and in the AC case, those line limits are this curved, this curve, and the feasible region is the area underneath that curve. While in this toy picture, then using a DC model or some sort of linearized model means that I'm using one or another of these two lines as representing the feasible set. So in the top case, where I've set the horizontal line up here at S0, I am accepting infeasibility some of the time, right? So maybe my solution winds up here, and that's outside of the AC optimal power flow feasible region. So I'm accepting infeasibility some of the time. If I use this other approximation, it's a little more conservative. I've tightened the line limits. Well, then I'll be suboptimal some of the time, right? So in the sort of easier conditions, I'll be missing this potentially more efficient operating point. So the idea is that using this less accurate DC model requires either accepting infeasibility or sort of being more conservative and accepting suboptimality, or some combination of both. So what we have seen in this competition is that almost all of the successful solver entrants used an NLP-based AC optimal power flow really at the core of their algorithms. I don't know for sure actually that any relied on DC on DC alone. So then I want to talk a bit about AC within a unit commitment algorithm. So one can make the claim, and I've heard it made, that current ISO procedures really do solve an AC unit commitment problem. And I think what is meant by this is that they obtain a solution in their unit commitment process that is feasible to an AC problem. So I don't understand this statement to mean that they have built an AC unit commitment solver and are running that. I understand it to mean that they've built a unit commitment solver with a DC model and then evaluate AC feasibility. And if there are some violations, then they eliminate those violations in one way or another to ensure that the solution that they get is AC feasible. And I would say I understand it further to mean that it may not even be the solution that they get out of the unit commitment model that is claimed to be AC feasible, but that after the unit commitment model is solved, one does a further solve with some sort of AC power flow, AC optimal power flow model, and that then that solution is combined with the unit commitment solution, and one obtains then a feasible solution to an AC unit commitment problem. So I can see that one is obtaining a solution to an AC unit commitment problem. I don't know that that in current practice we're obtaining an optimal or even a close to optimal solution to an AC unit commitment problem. And ultimately, what it sort of comes down to is in the stage where you're adding constraints to fix the violations that might have been observed. We're adding linearized constraints, and so again, those are either accepting suboptimality or feasibility, or some combination. There is another issue that I want to highlight here, and that is the selection of constraints to be put in the initial DC unit commitment model. And so this sort of harks back to one of the previous speakers. Knowing which constraints to put into this initial model is important for the performance of an algorithm like this that adds constraints iteratively. So if you can get close to the right set of constraints at the very beginning, then you don't have to do very many iterations, and it solves efficiently. So I think that there's a concern about the difficulty of that problem of estimating the initial set of security constraints. And I think that problem interacts with AC considerations and interacts with changes that are occurring on the power grid, such as more wind and solar power. So maybe we'll be able to say more about that later.
Hey, Jesse, you have 4 minutes left.
Goodness, okay. All right, so there's one, I think I want to skip to something that I haven't spoken about in a while. There we go. Okay, so one of the features that we worked on in Challenge 1 especially, that I found especially interesting in the competition, was this idea of post-contingency local control. So the main idea is that the real and reactive power output of generators immediately following a contingency might not be entirely under control of a dispatch, right? So the dispatch, which is sort of the main thing that we're trying to solve with the ACOPF problem, the real power output, the reactive power output, all that we can call on the generators to follow that dispatch. But then what they do after a contingency is not something that we can put into a dispatch. What we can do though is assign them a control algorithm that responds to conditions like voltage or frequency. And so what we were doing in this part of the model is trying to model the fact that after a contingency, generators are following some kind of control algorithm. So what we did is, I think, a first step toward modeling the control timescale in optimal power flow. The constraints that we put in to model this wound up being, in one way of modeling, wound up being complementarity constraints, and that imposed some interesting computational challenges on the solvers. So to sort of briefly look at this, here on the upper right is how reactive power output after a contingency was modeled. And so the idea is that the pre-contingency voltage at a generator is this variable VI, and then the post-contingency reactive power output of the generator depends on whether the post-contingency voltage is either above the pre-contingency voltage or below it. The idea being that the generator is following a control algorithm to try to keep its voltage as close to the pre-contingency value as possible. So the pre-contingency value is acting as a set point. And then the behavior is that the reactive power output has to try as hard as possible to maintain the voltage to that set point. So if the post-contingency voltage is too low, that is, if it's below the pre-contingency, then the reactive power output must be at the Q max of that generator. And if the post-contingency voltage is too high, that is, it's above the pre-contingency value, then the reactive power output must be at the Q min value. So one can model that in any number of ways with integer variables or with algebraic constraints. And I've written a formulation of it as sort of complementarity constraints, but that's just one way of writing it down. It was really up to the solvers to decide how they handle that. For real power, it was similar, I guess, but maybe a bit more complicated in that there's an idea of the generators are responding to a system-wide power imbalance, and that could be a representation of low frequency, and that each generator has some constant of proportionality that tells how much of that imbalance that generator would respond to. And then so the generator has to follow that response, and that's this red line, up to its P max value or its P min value. And if it gets to there, then it can no longer follow that proportional response, and it has to just get stuck at its limit. So that was I really enjoyed the algebra of coming up with that model and getting to see how solvers responded. Okay, so I can stop there and thank you.
Anyone have any questions for Jesse? Thank you, Jesse. Do we have anything online?
Just a thank you.
Oh, I think, Shmuel, did you raise your hand? I saw a hand go up. No? All right, well, thank you all, and thanks again, Jesse. Oh,
Is
wait.
it Oren?
One second, yeah. Go ahead.
Go ahead.
I assume that's Shmuel Oren, but it could be a different Oren. You have your hand raised. Go ahead, you can unmute yourself.
Can you hear me now?
Yes.
Yes.
Yeah, go ahead.
Yeah. My understanding is that most ISOs, they deal with the AC part by some form of successive linear approximations. The data in the Go competition kind of disadvantage such approaches because you allowed phase angle differentials that are substantially larger than what's common allowed in software, and that gave an advantage to NLP approaches, and those phase angle differentials that you allowed were kind of unrealistic.
So, thank you, Shmuel, for that question. I think that, so in my mind, that really begs the question of, are there circumstances where we can expect that we will see greater phase angle differences? And I mean, I would call that stressed conditions. So do we expect to see conditions like that more often in the future for any reason? And I think I have heard the argument that we can expect to see that more often due to wind and solar participation in the market, essentially.
So you think that, I mean, what the ISOs are doing by essentially constraining the phase angle differentials, that results in suboptimal solutions? So
I'm making a hypothesis to that effect, and that not so much that what they are doing or what they have done was problematic, but that it could become more problematic as conditions in the electricity industry change towards a future with more renewable energy.
Okay.
And that was one of the sort of main justifications of really of the ACOPF having a competition around it.
Well, I mean, everybody, I mean, as I say, people are taking into consideration the AC aspect, except that given the current, methodologies, they are able to get away with successive linear approximations.
Yes.
And you made it essentially kind of impossible by relaxing those phase angle boundary constraints.
Oh, well, so we didn't. I think I see a different side of what you're saying. So we didn't impose any phase angle constraints at all.
Yeah, I know, but that's the point, that by imposing constraints, that makes it,
Right, but so we did not, though, we did not prevent competitors from imposing their own phase angle constraints if they found that useful to finding a solution, right? So we did not rule out a solution algorithm that would rely on linear programming and successive.
Anyway, it's worth noting that was one of the things that gave, because you say that all the successful teams were using NLP, like POCP and all that, and that kind of was the cause, the reason that made the NLP more successful, that because the traditional, what's customary to impose phase angle constraints, difference constraints, were relaxed.
But do you think that a competitor could have designed their own phase difference constraints and then I mean the question is, by adding those constraints themselves, they might have cut off not just the optimal solution, but they might have cut themselves off from a good solution.
Yeah, to restrict the problem. Anyway, thank you.
Thank you.
All right, so with that concludes day 2, at least in this room. I'm not sure if they're still going over there. Thanks again, Jesse, and to everyone who spoke in this session. And we will restart at 9:30. Are we doing 2 tracks?
No, just one.
Okay. So we hope to see you tomorrow morning, and thanks again, everyone.